Hello, everyone. Welcome to the June 2022 Ask Me Anything edition of the Mindscape podcast. I'm your host, Sean Carroll. And as many of you know, if you're listening in contemporary times, mid-2022, and you're a podcast listener, you know that I am in the midst of moving from the West Coast to the East Coast of the United States, from Los Angeles to Baltimore, from Caltech to Johns Hopkins. It's a lot of work moving, finding a house, packing things, all sorts of things. As you grow older, you accumulate more stuff. And we got to move our stuff into a new place. So anyway, the point of me mentioning that is I have no amusing anecdotes to begin this AMA with. I just got to try to squeeze out time to answer the actual questions that were put in front of me. So let's do that. Let's go. Dan O'Neill says, do you think that the concept of emergence could be useful in advocating for abortion rights? In this case, the idea that a human being is an emergent phenomenon that develops gradually through the course of gestation. To someone who believes that a human person with full legal rights comes into being at the moment a sperm fertilizes an egg, or at some other very early stage of pregnancy, the mother's right to privacy or control of her own body will never justify what they consider to be first-degree murder. It seems to me that the profound question of what is and is not a human person should be addressed more directly by the pro-choice movement. So when I first read the very first sentence of the question here, do you think that the concept of emergence could be useful in advocating for abortion rights? I was thinking this is not worth answering, but in fact, this is a great question, the way that it developed. So thanks for asking this, Dan. And it's something that I've addressed in not quite these terms, but elsewhere in blog posts and things like that. I don't think that emergence is the central issue here, but the nature of what is a living being is absolutely central, and emergence has something to do with that. But really, the distinction here, as far as I can tell, is not so much between, how exactly does emergence happen or something like that, but physicalism versus some kind of dualism, right? Do you think that human beings are collections of particles obeying the laws of nature, or do you think that there is some fundamentally distinct essence that inhabits them and gives them a soul or a mind or something like that? That would be the dualist perspective. And of course, many religious traditions believe exactly that. Many scientific traditions are much more physicalist about things. It's a very hard discussion to have with people, right? But I guess what I want to say is I do agree that we should have the discussion. So yes is the short answer to what I take to be the spirit of your question. The way that I put it in my blog posts is that ontology matters to discussions of public policy, and this is exactly a case. So to step back a bit from the specifics of the abortion debate, we have a way of generating laws and policies in our democratic republic that involves morality, involves values. I mean, of course it does. How could it not? We try to have policies that lead to good outcomes. Well, what does that mean, good, right? You have to have some normative component of your thought there. You have to have some way of judging what is good and what is bad. That's values, that's philosophy, that's morality. And yet we disagree about some very fundamental issues within the realm of morality. This has been, and always will be the fundamental challenge of democracy. To live in a democracy, you have to, on the one hand, have some common values, right? You have the people who live in the democracy have to have some things in common so they can get along. But on the other hand, be willing to live with disagreement about some other fundamental values and make compromises, right? That's what democracy is all about. And when it comes to, life and death, sometimes people are not willing to make these compromises, so it becomes hard. It becomes a challenge to the very notion of democracy. Having said all that, so anyway, short answer is yes. I think that we, in practice, make a bunch of laws based on some very vague and hand-wavy and disreputable ideas about morality. I mean, the morality is there, but it's not very sophisticated. It's not very careful. And many of the ideas that we have would not stand up to closer philosophical scrutiny. I would like those discussions to be at a much higher level, much more sophisticated, and much more informed by how we think about these things at a philosophical, moral, ethical, etc. level, not to mention an ontological level. But there's also the fact that I think that it's not really true that a lot of opponents of abortion consistently hold this point of view. Some do, many do not. This has been pointed out many, many times. If you really thought this was true, you would literally convict people of murder for doing abortions. And furthermore, there's plenty of times when people miscarry or otherwise a fertilized egg does not come to term as a healthy baby. And what do you do in those circumstances? Furthermore, if you cared all that much, you might want to care about the lives of these children after they were born, as well as before they were born, and so on and so on. There are various things that, it's too long a discussion to go into right now. There are various reasons why people are on the anti-abortion side of things, other than some principled philosophical idea about dualism and the ensoulment of the person at the moment of conception. That's just something to keep in mind when you have these discussions. If the point is we should be more honest in our discussions, that's got to be a component of it. Kyle Stevens says, can consciousness only perceive a single direction of time? If I were to create a simulated world that was able to run forwards and backwards in time, could a hypothetical conscious simulated observer in this world perceive the direction switching? So the short answer is yes, consciousness can only perceive a single direction of time. There's probably footnotes there, and it becomes complicated because the world only has a single direction of time. So whenever we talk about these questions, we're extrapolating our knowledge beyond the actual world, which is always a dangerous thing to do. But the deeper answer is you have to sit down and really think about what you mean by the direction of time. So you say, could a hypothetical conscious simulated observer perceive the direction switching? What does it mean for the direction of time to switch? Do you mean that the entropy of the entire system is going down? Because that doesn't just happen, right? I mean, there's no way that in the laws of physics, if entropy has been going up for a long time, it can start going down in the whole universe and then start going back up again and then start going down. That's just not things that happen. So it's sort of a hypothesis contrary to fact situation. Roughly speaking, our consciousness as a process through time depends on the increase of entropy. So roughly speaking, if entropy were going down according to someone's directionality in their time coordinate, then consciousness would perceive the direction of lower entropy as the past and the direction of higher entropy as the future, and they would always live in that direction of time. So the short version of that statement is consciousness always perceives entropy to be increasing along what it calls the direction of time. But even that is not, you shouldn't take those statements too seriously because there are different ways for entropy to increase and decrease. If you are not a closed system, but an open system as part of a bigger system, your entropy can go down without any reversal in the arrow of time. If you're a closed system where entropy is going down, then you would perceive the arrow of time the other way. All of which to say it's very complicated and very far outside our everyday human experience. So you just have to think really carefully about what you mean by these questions. Okay, I'm going to group two questions together, also about the arrow of time, but they're going to bring in many worlds. So Brad Malt says, could many worlds explain the arrow of time? That is, once the world has split, I assume it cannot come back together. Otherwise, multiple copies of oneself would need to be merged. So, doesn't the proliferation of worlds in a unidirectional manner imply that time can only evolve in one irreversible direction? And then Robert Ruxandrescu says, would taking the many worlds interpretation seriously fix the low entropy at the Big Bang problem? After all, we're just in one of the possible branches of the decay of the inflationary period, which is a radioactive quantum process. There are probably countless of branches in which the entropy is high and no living beings exist. We simply find ourselves in one compatible with us existing, so basically an anthropic reasoning. So in both cases, the answer is no. Many worlds cannot explain the arrow of time or the low entropy at the Big Bang, not by itself. I mean, I think that many worlds is right, so whatever the right explanation is will be compatible with many worlds, but you can't just say many worlds, therefore an arrow of time, in any simple, straightforward way. Otherwise, people would have said it. So to the first idea from Brad, yes, it is true that the worlds branch toward the future, not the past, but that's not an explanation for the arrow of time. That's because there's an arrow of time. It's because there's a special initial condition, that there was a small number of branches to start, and they branch toward the future. It's exactly the same statement as saying there was a small entropy and it grows toward the future. So you need to explain why there was only one branch at early times. That's the same demand of explanation that you usually have for the arrow of time. And likewise with Robert's question, could you explain the low entropy at the Big Bang? Here, it's a little bit different because you're saying, well, there's many different branches. Some of them entropy will go up, some will go down. We'll always find ourselves in the way, in a branch where entropy is going up in the right way. That's true, but it doesn't work quantitatively. It doesn't work at the level of actually explaining the world we observe, because the entropy of our Big Bang local universe was way, 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 way lower than it needs to be for any anthropic purpose. The entropy of the early universe was enormously smaller than it needs to be. And one reflection of that is, as it grows, right, as the universe expands and entropy increases, you make like 1 trillion galaxies. So you're taking the amount of matter that was in a low entropy state is enough to make 1 trillion galaxies, very, very roughly speaking. Why was there that much stuff in this low entropy state? You know, you could have had a universe that was much, much closer to thermal equilibrium, but maybe there was a fluctuation that made 1 galaxy rather than just 1 trillion, right? And then you'd be plenty able to make human beings or any other kind of life form you want, and such fluctuations into just 1 galaxy, or even just 1 solar system or a few solar systems, those are much, 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 much more common than fluctuations into our whole universe. I did write a paper, if you want to look it up, with Matt Johnson and Anthony Aguirre. Anthony, of course, was a former Mindscape guest, where we go into the details of what it would look like to fluctuate from thermal equilibrium into a low entropy Big Bang. It's very, very unlikely. You just basically wind the whole clock of the universe backwards. That's unlikely at every single step along the way. So Jimmy Summer says, I've heard argued that regardless of the crisis being solved, slowing progress should never be an option because there will always be more problems to solve down the line that will require that continued progress to solve. For example, climate change needs a solution, but in this framing, slowing down progress for the sake of reducing fossil fuel use would be counterproductive in the long run. I've heard arguments like this. In fact, in a slightly different context, Tyler Cowen, who was an early guest, made an argument like this. But no, I don't buy it at all. I mean, and part of it is just the statement being made is so hopelessly vague that it's impossible to argue for it being right or wrong, right? Slowing progress should never be an option. I mean, that's a rather grandiose claim. It depends, right? The details matter for something like this. So, I mean, I don't think it's true, but imagine that climate change were so bad that it was truly an existential threat to the very existence of human life, right? Maybe in the next 50 years, climate change literally wipes off every human being from the face of the earth. Again, I don't think that's a realistic worry, but maybe it was. And if it were, you can't say, well, let's just accelerate the rate of climate change because someday we'll find an answer to it, because you'll be dead before you can find an answer to it, okay? And that's a problem. I don't think that any simple-minded model like this is going to get you the right answer. These are complicated questions. You're going to have to think through the details a little bit more carefully. Jeffrey Segal says, I very much enjoyed your conversation with Nick Lane. At one point you mentioned biologists thinking of natural selection as a mechanism that improves things. But could natural selection be a form of the second law of thermodynamics? If increased complexity of life leads to increased entropy, then perhaps natural selection is nature's heuristic for increasing entropy in an ecosystem. Well, short answer is no. I don't think that's quite right. But longer answer is they are related to each other. But the relationship is that, I've said this before, the arrow of time, which is a result of increasing entropy, is prior to everything else, prior to every process that has a directionality in time, and that includes biological evolution. So biological evolution definitely has a directionality, right? We started with some single-celled organisms. Now we have a rich ecosystem. That's an arrow of time. The only reason why there is an arrow of time is because entropy is increasing. Therefore, you know instantly that without entropy increasing, you wouldn't get biological evolution and natural selection in the same way. The converse is not true. The converse doesn't even make sense, because you can't say, well, could you have natural selection without entropy increasing? Because, well, you can't say, what if you had natural selection without entropy increasing? Because you can't, okay? So, but the point is that entropy increasing is the first thing, the important thing, the prior thing. It may or may not lead to increased complexity and natural selection. Natural selection or other manifestations of complexity are one of the sets of things that can happen when entropy is increasing, but it's not the only way for entropy to increase. So the way to think about it is that the increasing entropy allows for the possibility of natural selection, but it doesn't cause it, and it's not, necessary in any way for entropy increase. I'm going to group two questions together about self-identity in many worlds. So Tony Runge says, if there are many worlds, is there reason to restrict the idea of me to just the world I experience? Are we like a tree with many branches but only experiencing one branch? And Peter Blankenheim says, you recently explained that we can map a universe-splitting decoherence event as spreading at the speed of light or as splitting the whole universe instantly and get the same predictions. I think you said this is because the many worlds are strong emergence phenomena and don't exist in fundamental physics. I also think you said that the many me's and the many worlds are each a real person with a real conscience, for instance, to the extent that people have real consciences. I'm not quite sure, Peter, if you mean consciousness rather than conscience, but maybe you do. Anyway, these two truths suggest that my personhood, knowledge of which many philosophers say is the primary and only unquestionable knowledge I have, is knowledge of something that does not exist in fundamental physics. Did I get that right? So that last part, yes, you got completely right. The point here is that personhood is not anywhere to be found in fundamental physics. As a statement, I would agree with that. I have to disagree with a couple things. The phrase strong emergence, which we'll talk about again later, is a specific, meaningful phrase in the philosophical context, and many worlds are not strong emergent phenomena. They're what are called weakly emergent phenomena. That is to say, they're just ways of describing what is going on at the microscopic level. The other thing to point out is that this has nothing to do with many worlds. Even if there was only one world, it would still be true that personhood is a higher level emergent phenomena. When you look at the laws of physics at the fundamental level, the core theory or the standard model or whatever, there's no persons in there, right? They are clearly higher level emergent ways of talking about what goes on in this complex world. To Tony's question, is there reason to restrict the idea of me to just the world I experience? Yes, there is. It's not like a tree at all. I mean, the set of all future copies of your present you is like a tree, but it's not exactly like a tree because the branches are out of contact with each other. And that is why you restrict the idea of you to each world. Once the other people are on other branches, nothing that happens to them affects you and nothing that happens to you affects them. There's literally zero sense in which those different copies of you constitute a coherent physical system. They are separate, non-interacting things. They're each a person. It's not like there are many copies of you and one of them is the real you. They're each many people, okay? And you are one and there are others who are others. That's the right way to think about it. So to go back to Peter's question, well, what about these philosophers who say that personhood is the primary and only unquestionable knowledge I have? They're wrong. I mean, I don't think there's any unquestionable knowledge that you have, but I certainly don't think that it's primary. It's certainly not primary when you consider the relationship of personhood to fundamental physics. Kunal Menda says, if I want to simulate a dynamical system, I would write its state derivative as a function of time and its state, and then integrate. I'm implicitly assuming, however, that time is an objective quantity when doing this. If I understand relativity correctly, then you cannot say the universe is in some state at some given time because it depends on the reference frame. I want to then know how Laplace's demon would dynamically evolve the universe. Do they have to assume a reference frame when doing so? Is there some invariance in the frame they could choose that makes it not matter? Yeah, it's exactly that latter bit. And you don't need to be Laplace's demon to do that. You can be any undergraduate doing a problem in a problem set in special relativity, right? You can still, in special relativity, solve equations, or in general relativity for that matter, for the evolution of the universe universe, starting with an initial state and integrating it forward in time. But there's an invariance, there's a symmetry, a relativity, if you will, that says that you can choose many different possible slices of space-time on which to frame your initial conditions, okay? Many different reference frames in which you could give the data that Laplace's demon would need to integrate forward in time. And that's perfectly fine. There's nothing in the original construction that required the way that you stated your initial data to be unique. Right? As long as you can state it once and for all in a way that is sufficient and necessary to integrate forward and backward in time, that's all you need. And relativity is saying there are many, many ways of doing that. That's fine. That shouldn't bother you at all. Jonathan M. Goodson says, I have questions about the familiar statement that the wave function contains all the information that can be known about a particle. What makes people think it's true? How confident are you in its accuracy? And how could one reconcile this statement with John Bell's well-known dictum that either the wave function as given by the Schrödinger equation is not everything or it is not right? Well, we don't know that it's true. There are people who think that maybe it's not true, that the wave function contains all the information that can be known. What we know is the following. If you know the wave function, you're able to make all the predictions for what the particle is going to do, okay? There is no one has ever come up with a way of making better predictions than the wave function plus the Born rule are able to give you. You're allowed, therefore, to only use the wave function and to say that contains all the information because there's nothing extra that you get from imagining more information. You're also allowed to imagine there is more information, but that more information is just forever hidden from you. That's what people do who like Bohmian mechanics, pilot wave theories, hidden variable theories, right? Personally, I don't see what is being gained by doing that, but you're allowed to do it. So how confident am I? Pretty darn confident, but certainly not 100%. Finally, Bell's statement about the wave function either not obeying the Schrödinger equation or not being everything, well, he was discounting many worlds. In Bell's theorem, there is an axiom, a postulate, a premise of the argument that says that measurement outcomes have unique values, which is just not true. In many worlds. In many worlds, measurement outcomes have all possible values just on different worlds. So it just doesn't apply. So, basically Bell is saying, assume many worlds is wrong, then many worlds is wrong. That's completely true, but it doesn't mean many worlds is wrong as an argument all by itself. Dan Inch says, recent global events are reminding us that nuclear weapons still exist. As I understand it, these weapons were developed fairly shortly after the underlying physics was discovered. How much of a risk do you think there is that modern physics has paved the way for something as bad or worse? Is there a dark matter bomb on the horizon or an Everettian bomb? I think that there's very, very tiny risk, to be honest. And the reason why is because, as I've talked about in other contexts, fundamental physics has passed a threshold. It has passed a threshold where the stuff of the world around us is accounted for by fundamental physics. The thing about nuclear weapons and radioactivity and fission and fusion was they were always there. They were always happening, right? Atoms are decaying in your body even before we knew about it. And the sun is fusing nuclei together and making power from them. That was happening before we figured it out, okay? So what we did was we figured out something that was there all around us and we put it to use in making bombs as well as making other kinds of technology. And now, since the laws of physics underlying our everyday world are completely understood, that's not happening anymore. We get the stuff that is around us. There will almost certainly be more stuff, be new physics that we invent. So dark matter is an example where we think that there's something there, but we don't know exactly what it is. But it is very, very, very hard to imagine putting it to technological use. Why? Because you can't touch it. You can't manipulate it. It's not. If you could, it would be around us. It would be here on Earth, and you could find it fairly easily. Dark matter doesn't interact with ordinary matter, and that's not a feature you want in a bomb. Like if you're going to make a bomb, you want it to interact with ordinary matter in a fairly dramatic way. Likewise, for Everettian quantum mechanics, it's just quantum mechanics. The predictions for the real world are exactly those of quantum mechanics. So it doesn't really give you anything new. That insight doesn't give you any technological handle. Of course, that could be wrong. It's possible that there is something that is unanticipated that will be a future physical understanding. And that's always true. I mean, that's sort of a mindless, cheap thing to say. The non-trivial thing to appreciate is how fundamental physics has passed this threshold of really understanding the world around us. And therefore, the low-hanging fruit has been picked when it comes to technology. Even when it comes to like modern, speculative technologies like high temperature superconductors or quantum computers or things like that, those are still based on known physics. They're not taking advantage of new physics. So I completely think that there will be all sorts of surprising new technologies. I just would not be surprised if they were not based on physics that we haven't yet developed, fundamental physics that we haven't yet discovered. Bob Weinman says, as I recall, Feynman had a very low opinion of philosophy. If you had the opportunity to try to get him to change his mind, how would you begin? Well, I mean, the short answer here is that I wouldn't. Like, I don't care. There's lots of people out there who have a low opinion of philosophy. There's lots of people out there who have low opinions of physics or of other things. Let them live their lives as long as they're not bothering me. If they start bothering me, then it's a different thing. The section of people who matter for a question like this are not those who just say, I have a low opinion of X. It's those who say, I think my opinion of X is low, but I'm not sure. Explain to me why I should have a better opinion. Then that's a person you can talk to, right? That's a person who you can have a dialogue with. They're asking a question. They're interested. Once people's minds are closed, then forget about it. Move on to more greener pastures, right? I think it's a pretty easy, if you did have, if Feynman or someone said, look, why do you care about this stuff? I'm sincerely interested in it. All you have to do is read Feynman's books to see whole bunches of philosophy, right? It's not that hard. He might also at the same time be talking out the other side of his mouth and poo-poo philosophy, but he was doing it all along. He wrote a book called The Character of Physical Law. How much more philosophical can you get than that? And he was really good at it too. If you read the Feynman lectures on physics, you'll read a very clear statement of what we would now call the Boltzmann brain problem, the need for a low entropy initial condition near the Big Bang, which many other people did not appreciate. And what I would point out to him is that the people who do appreciate it now do so largely, although not exclusively, but largely due to the efforts of philosophers, not the efforts of physicists. There is a role for sitting and thinking carefully about the underlying logical conceptual structure of your physical theories, and I don't think that's a difficult case to make. Justin Bailey says, if every particle is an excitation in a quantum field, can we say there are really only 12-ish fields in the universe that make up everything? Well, it depends on how you count is the frustrating answer. So think about an electron, right? You can say, so I know where you're getting the 12-ish from. Just count the number of particles or whatever, right? There's more than 12, even in the standard model, because there are 6 quarks and 6 leptons. But then there's also bosons, right? There's the gauge bosons, and they count. Those are particles too. So I don't know how many there are, but there's certainly more than 12. But even if you take one of them, like the electron, right? When you say there are 6 leptons, one of those leptons is an electron, right? In the usual way of talking about the standard model. But how many fields are there that you need to describe an electron? You might say, well, the electron field. But the electron field has a spin up component and a spin down component, or a helicity right-handed or an helicity left-handed, if you want to be slightly more technical about it. So there's really those two components. And you can't really completely clearly distinguish the electron field from the anti-electron field, right? When we say there are 6 leptons, we're grouping together particles and their antiparticles. So mathematically, the field that describes electrons comes with 4 components, which you can think about as spinning clockwise, spinning counterclockwise, electrons, and positrons. 2 times 2 is 4, okay? Likewise, for quarks, they have the same kind of story, except they also come in 3 colors, right? So there's a whole bunch of fields, but then it depends on how you count. And there's no right way or wrong way of counting. When you have a vector pointing in space, like the electric field, is that one field with a vector value, or is it 3 fields because the vector has 3 components? Who cares is the answer. It doesn't matter, but the spirit of your question is, are there only some small number of fields that make up everything? Well, not everything, because there could be fields that we haven't yet discovered because they don't interact very strongly with the stuff that we do have in our laboratories, like the dark matter, right? Dark matter is probably some excitation of some quantum field that we just don't know which field it is yet. So it might be some relatively finite number, but we don't know what that number is right now. Joachim says, in the spirit of the very effective method of, in order to solve a problem, imagine you have already solved it and work your way backwards, I would like to ask you, imagine you have fixed the climate problem. How did you do it? I'm not an expert on this, so you shouldn't take my recommendations or anything like. Well, you shouldn't take my ideas as recommendations. Let's put it that way. I'm a theoretical physicist, not a climate scientist or engineer of any sort whatsoever. But at the level of theoretical physics where everything is a spherical cow, here's the basic problem. We've had millions of years of life on Earth creating what we think of as fossil fuels, right? Oil and gas and coal and stuff like that, out of the biological organic materials that were put underground, over the course of, again, many millions of years. And this is a very finite resource. It's a very valuable resource because these are complex molecules. A feature of life, of biological happenings, biological organisms, is they create much more complex molecules than inorganic processes do. So, and there's only a finite amount of it, not just burning, but there's other things you can do with these fossil fuels. You can make plastics and other materials. They're crucially important for scientific research and so forth. And we are literally burning them, right? This very finite resource, we are literally setting a match to it and lighting it on fire. And I get why you have to do that early on in technological development, but we don't have to do that anymore. We can save some of that resource, which is why I'm not in favor of burning through it faster, which is a lot of the strategy for, having fuel be cheaper and so forth. Dig up more, drill more, have more pipelines. That just burns through our finite supply much faster. And if you think, well, it's finite but still pretty big, you're wrong. That's the traditional mistake. The oceans are very big. We can't make them dirty, right? It's not really true. We can do it if given a few years. So I would not have any fossil fuel burned at all. If you're thinking about the ultimate solution to this problem, stop burning fossil fuels. Do other things. What are the other things? I don't know. Some combination of renewable energies, fusion, nuclear power, whatever it is. Again, they're difficult technological engineering problems that I'm not an expert on. So that's a long-term solution, right? That is not a short-term solution. In the short term, we have to have a path to get there from here. One simple thing is just to, shift from using machines that burn fossil fuels to using machines that run on electricity. Put a lot more technological development into batteries and electrical power generation, etc. Having said all that, there's also the entirely different possibility of cleaning up the atmosphere, right? If it's really climate change in particular that you care about, you can imagine, again, it's easy to imagine, it's hard to build, but you can imagine all sorts of either chemical or biological ways to remove hydrocarbons or whatever from the atmosphere. That could very well help. I don't know what the prospects are for that. I'm, again, not an expert. It does not solve the problem that we have a finite amount of fossil fuels here on Earth that we're burning through like crazy. So I'm all in favor of trying to imagine technologies and create them that would clean up the atmosphere. But if we just keep burning our oil and gas and coal, that will not be by itself a solution. Sid Huff says, it seems that most theoretical physicists believe that gravity is fundamentally a quantum phenomenon, but no one has actually figured it out fully. Is it possible that gravity cannot in fact be quantized? What would the implication be for the standard model? Well, as I've said before, any question that begins, is it possible? The answer is almost always yes. Sure, it's possible that gravity cannot be quantized. There's a very trivial sense in which I think that gravity is not the thing that should be quantized. You should have a quantum mechanical understanding of nature from which gravity emerges. But I think that's not what you're pointing at. Probably what you're imagining is gravity, which we think of as the curvature of space-time, post-Einstein. Gravity is the curvature of a classical space-time, and quantum mechanical things happen within that space-time. That's what we call semi-classical gravity, right? If you imagine you keep space-time classical and have quantum mechanical things going on inside it. The question is, maybe is that enough? Could we get by with a purely classical spacetime and only have matter be quantum, but living in that classical spacetime? And there's plenty of reasons why the answer is almost certainly not. You never know for sure. In physics, that's how it goes. Some brilliant person might be able to find out how to do it. But basically, the answer, it doesn't seem to make sense. It doesn't seem to map onto how we think about gravity working. So the classic example is, do a quantum mechanical experiment where you split a wave function into two different pieces and use that to actually create something where the wave function of something big and macroscopic with a gravitational field is literally in two different places. Okay, this is it's easy to do in a cheap way. It's hard to do it carefully. What I mean by that is I could easily just measure some spin and then move a bowling ball left or right depending on what measurement outcome I got. But then if you believe that wave functions really collapsed and so forth, you wouldn't believe that the bowling ball itself was in a superposition. So what you would really need to do it completely carefully is have an experiment where the wave function of the bowling ball was not interacting with the outside world, was not measured in any way, and yet was separated into two different locations in space. And then measure the gravitational field of the bowling ball. Where does it point? Does it point to in between where the two pieces of the bowling ball and the superposition are? Or does measuring the gravitational field cause the wave function to collapse in some way? Again, we don't know what the right answer would be, but the rough feeling is that whole picture doesn't make sense. All of our familiarity with gravity comes from situations where the gravitating objects have specific macroscopic locations. It's hard to imagine what to do if your gravitating objects didn't have large macroscopic locations, specific macroscopic locations, right? If your gravity was classical, how does it respond to quantum mechanical matter? Again, I'm not saying that it's impossible to imagine, but it'd be very, very different than anything that we have in physics today, and it'd be hard to figure out how to make it work. P. Walder says, in your recent Mind Chat discussion, Mind Chat, different podcast than Mindscape here, but I was on a Mind Chat with Philip Goff, Keith Frankish, and Barry Lower. So the question is, an issue was raised regarding whether physics acts differently in the brain as compared to lab-based environments. In that discussion, locality was identified as a principle that might prohibit the known laws of physics acting differently within the brain, regardless of its complexity. In his solo follow-up podcast, Philip insisted that he would not expect strong emergence to be present in lab-based particle experiments because the environment was not a complex one, and these lab-based observations could not exclude the idea that strong emergence could be present in the brain due to its inherent complexity. Could you comment on this? Sure. Philip, who I've had on the podcast before, Philip Goff, is a panpsychist, and he doesn't believe that physics all by itself is going to be enough to explain consciousness, which is fine. And I give Philip enormous credit for engaging with people who disagree with him about that. But he just doesn't understand physics very well. That's okay. I don't understand neuroscience very well. I don't even understand whole bunches of philosophy very well. And so for Philip, it's very easy to say, imagine changing the laws of physics in some dramatic way that shows up inside a brain but not inside a rock or inside the Large Hadron Collider. To those of us who understand physics pretty well, we appreciate how difficult that would be. Again, just as I mentioned a couple of paragraphs ago, you can't say it's impossible. That's not how physics works. Maybe it's possible that the behavior of an electron is different if that electron is embedded in a brain versus being embedded in a rock. My point is that it is completely incompatible with everything we know about physics, locality being the most obvious incompatibility, in the sense that the way the laws of physics work, according to the core theory of contemporary physics, is that the electron field at every point in space only responds to what other fields are doing at exactly the same point in space. It literally does not care at all about what fields are doing elsewhere, except insofar as they help determine what the other fields are doing at that same point in space. That is just a bedrock feature of quantum field theory. That's what quantum field theory is in some very real sense. So you're perfectly allowed to say, well, maybe it's not like that in a brain. Now, number one, there's zero motivation in physics to do that. All of your motivation is from philosophical thought experiments. And in my mind, the fundamental physics understanding is enormously more sophisticated than the philosophical thought experiments are, so I trust them much more. But the other is that as soon as let's put it this way, you can't it's not okay to just say, well, maybe let's be non-local. Let's just violate that cherished principle of physics. That is completely meaningless unless you do it, unless you write down a theory. This is how physics works. You write down a model, you write down the equations according to which you would modify ordinary physics to allow for this sort of non-locality. And the reason why you need to do that is not just because it, makes you a bit more honest, but because almost inevitably, when you do that, everything will break. Everything that we know about how physics works will stop working, like information moving faster than the speed of light, right? If I can poke a field at one point in space and instantly have a reaction somewhere else, which is what you need if you're not being local, that's information moving faster than the speed of light, which could lead to all sorts of bad things, like how fast does it move? Clearly, you violated Lorentz invariance as well. Clearly, you're violating special relativity. The obvious implication of that would be all sorts of experimental craziness that would be very easily ruled out. But I can't tell you what that craziness is until you've written down a model, right? So no physicist is really going to take this very seriously at all. Finally, something worth noting is it gives you precisely zero progress on the hard problem of consciousness, right? Once you've adapted the laws of physics from the local form that we know and love to some non-local form, there's still laws of physics. There's still physical stuff doing its physical thing. I don't see what the possible motivation for breaking all the laws of physics is to make absolutely no difference to the problem that you're trying to approach. That would be my answer. JM Autobot says, I'm trying to better understand how the universe has a shape. I sometimes read that the universe might have pinched off a larger universe like a drop from a glass of water, or that universes might be like bubbles of soap, maybe even colliding in the past. Then I read how our universe seems flat by our best measurements. Can you help me understand how the universe can be both bubble-like and flat, especially if it is infinite? Thanks. Sure. The answer is we don't know what the shape of the universe is. It's extremely possible, again, we don't know, but it's extremely possible that the shape of the universe is just wildly different from place to place, that it has no simple form like flat or spherical or anything like that. Those are all simple ideas that you can propose and think about, but there's no empirical evidence for it. The empirical evidence is that our three-dimensional space within our observable universe is spatially pretty flat. Okay, but we also know with very, very high confidence that that's not the whole universe. The universe continues beyond what we can see because we can only see back a certain time to the Big Bang, right? It's conceivable that literally just now we're seeing the edge of our universe, but there's zero reason to expect that. It's much more likely the universe continues on. Maybe it continues on keeping flat. That's possible. Maybe even though our universe looks flat to us, the three-dimensional universe in which we live, the three-dimensional space, maybe it looks flat, but just because we're only seeing a really tiny part of it. Just like your yard could look flat even though the Earth is round, right? Maybe the universe is like that, and the universe looks flat to us, but is curved on larger scales. Furthermore, all of these words and whatever, bubbles and bubbles of soap, colliding and so forth, these are all kind of metaphorical, colorful things that people put forward. You got to be careful with what you mean. These colliding bubbles that people are talking about, what is colliding is the edge of the bubble. So it's very possible that our universe is inside, our three-dimensional universe is inside some two-dimensional bubble, which will someday collide with the boundary of another three-dimensional region of space that is also a two-dimensional bubble. We have no idea. I mean, we have speculations along these lines. It may or may not be true, but That's the edge. That would be the edge of our region of space. That would not be the region of space itself. So keep your wits about you, and be very careful when people are talking about this stuff to try to distinguish what we have evidence for from what we are speculating about. It's fine to speculate. I do it all the time, but be clear when you're speculating versus when you're talking about things we actually have evidence for. An onion has a priority question, and the priority question is in the form of a poem, which I guess I will read. The reductio ad absurdum of the botanical project in the field of insanity strikes an elegiac note. Conjectured latent variables roam unseen even in corridors, snared and prowled for dreaming, till each flash or burst be an assigned edge, the same or like as are to nip clouds in scud. Lamb winds of unfortunate gusts and uncalf us for the straying poles. One day, the basic unit will no longer be absent, a fine mesh fence and pure, tender quartering veins, no nodes barred. There's a question mark at the end of that, but I have no idea what the question is. So I will take my recitation of the poem as fulfilling the promise of the priority question there. Thank you for your poem, Onion. Liam McCarty says, if I understand your Mad Dog Everettianism approach correctly, your hypothesis is that the universe is exactly a vector in Hilbert space, and your goal is to derive all known physics from a spectrum of the Hamiltonian. I'm curious as to how you think about time from this perspective. Is it fundamental or somehow emergent? Well, the short answer is we think of time as fundamental, but it's not because we have some conviction that time is fundamental. It's just because, one step at a time. We're trying to make sense of some very difficult problems where experiment is not being much of a guide, and we have to, use our principles and our theorizing, etc. So I'm in favor of making as few wild leaps into the unknown at a time as possible. So it is completely possible in my mind that time might be emergent, not fundamental, whatever. But that seems to be, according to everything I know, a different question than whether space is fundamental or emergent. Quantum mechanics and quantum gravity really seem to treat time and space differently. Now, obviously, our best classical theory of gravity is Einstein's general theory of relativity, where space and time are combined to make space-time. So that is something to be kept in mind when one is trying to go from the quantum theory of gravity to classical space-time. But it's not any kind of immovable obstacle in the road. It's just an issue you'll have to keep thinking about as the future goes, as you develop the theory more and more in the future. Tim Giannitsos says, in computer science, space and time are considered two resources that a computer uses to make a computation. However, the third resource is randomness. No algorithm can actually manufacture its own randomness. If there is true randomness, it is always mined from the physical world. Space and time are associated into a manifold called space-time. Are there theories that incorporate randomness somehow as another component of this manifold? I think that this is an intriguing question that I don't know a simple, glib answer to because I'm not exactly sure what it would mean to incorporate randomness in this sense. There certainly are theories of quantum mechanics which are truly random, which think of the evolution of the wave function as something that has a completely stochastic component. I'm not sure. What I guess I'm not sure about is the extent to which this should be considered a resource, because the universe is not really doing a computation, right? The universe doesn't have an answer that we're looking for in any obvious sense. But maybe there's some role for that. I'm just not sure how to analogize it to what computer scientists think about. So I know that was a very unsatisfying answer, but that's the best I can do. What I want to do is tackle the next couple of questions. I'm going to group some other questions together because they're along a similar lines as to Tim's question. It's sufficiently different. I didn't want to group it together, but with a similar set of words appearing in them. So 3 questions to be grouped together. Roland Person says, if everything that will ever happen can be predicted by deterministic laws of physics, how can entropy increase? Wouldn't it mean that everything that will happen was already encoded in the initial state of the universe? I read some argument that if quantum mechanics had some truly random probabilities in it, then that could be a source of actual new information that could increase entropy. In this interpretation, the future would not be predictable. Douglas DeYoung says, assuming many worlds from the point of view of Maxwell's demon, is the Shannon entropy, the total information content of the universe, static? I imagine a universe where there is a momentary state and there are laws that then process this state into subsequent states, but do not increase the Shannon entropy. This somehow seems at odds with such an informationally rich universe we live in. And then Rob Greiber says, does an ever-ready interpretation of quantum mechanics suggest that as the universe approaches an era of proton decay in the distant future, there will be fewer worlds created? That is, are there fewer interactions that create wave function collapses as the entropy progresses or complexity declines? Is this another way of saying that as entropy increases, complexity increases, then declines? So what I take to be the common thread of these questions is that the way the universe explores the space of possibilities is a little bit different if the evolution of the universe has a random component to it. So if you think about, hypothetically, a set of laws of physics that were completely deterministic. So just to answer the many worlds aspect of this, in many worlds, of course, the underlying equation is the Schrödinger equation, which is completely deterministic. But observers don't see deterministic evolution in many worlds. They better not, because experimental evidence for quantum mechanics includes randomness, right? And that's exactly what many worlds predicts. It predicts that people on branches will see what are effectively random, unpredictable processes, or at least processes that are predictable only up to the Born rule for the probabilities of seeing things happen. So in quantum mechanics, forgetting about the fact that the wave function of the universe evolves deterministically, individuals see random events. And I think that this does count as sort of giving the universe a little extra oomph in terms of exploring the space of possibilities. If the universe were completely deterministic, to go back to what I started saying, if there were completely deterministic rules, not only for the wave function of the universe, but as seen by observers, then, to Douglas's question, everything that ever happened in the history of the universe would be encoded in the initial state, right? The initial state would be, in principle, to Laplace's demon, etc., able to exactly predict what happens in the future, and therefore it has all that information is in it. So if you just calculated the Shannon entropy in the most naive way, it would be a constant. It would not increase because the Shannon entropy tells you how much information you have about the universe. Now, none of us is Laplace's demon or Maxwell's demon or any of those demons, so we don't have that information, but in principle, it would be there, okay? When people talk about the entropy of the universe increasing, they're not talking about the Shannon entropy. There are different notions of entropy. They're talking about the thermodynamic entropy or the Boltzmann entropy. That is to say, imagine the microstate of the universe. There are many macroscopic configurations that have the same microstates associated with them. And as time goes on, we move from macrostates where there's only a small number of microstates to macrostates where there are large numbers of microstates associated with them. So the reason why you can reconcile the increase of that kind of entropy with the constancy of the Shannon entropy is that even in the current macrostate of the universe, which has a larger Boltzmann or thermodynamic entropy than the early time does, there is something we know about the current state of the universe over and above its current macrostate. Namely, that it came from a low entropy past. That extra fact, that extra piece of information we know tells us that the actual microstate of the current universe is living in a tiny, tiny, tiny subset of all the possible microstates compatible with our macroscopic information of only the current configuration, okay? Anyway, so for all intents and purposes, information is not really conserved because we don't keep track of all of those things. And quantum mechanics does jiggle things around. So it no longer is true in quantum mechanics that if you told me the exact initial state of the universe, I would predict what observers would see in the future, right? Now, ultimately, to get to Rob's question, they would all see the same thing because all of the worlds will eventually equilibrate, right? The space expands, stars decay away. In the different worlds, stars and galaxies are located at different places, different locations in space, but ultimately the stars go away. They fall into black holes, the black holes evaporate, so ultimately they go to the same equilibrium state. This is exactly the same as saying that if you put a drop of food dye in a glass of water, As it is beginning to fill the glass of water, each path that it takes, if you do it many times in a row, will be different, right? The individual swirls of complexity as the ink and the water mix together will be different if you do it twice in a row, but the eventual final state is the same, right? And so entropy increasing is exactly, to answer Rob's question, driving this initial increase in complexity and then diminishment in complexity. I think I answered Roland's question, just to be perfectly clear about it. In some sense, there is new information there. You could imagine a classical world. Let's put it this way. Infinity is very big. And in classical mechanics, the position of a single particle is given by a real number. That's an infinite amount of information. So if you had 10 to the 80th atoms, like we have in our observable universe, in a classical deterministic universe, you could still put an enormous amount of information into the initial state, okay? So it's not that you can't fit it in there classically and you need quantum mechanics. The new thing is the following. In quantum mechanics, you can imagine that the initial state is truly low information. Information in the sense that it doesn't take a lot of information to specify the initial state. So classically, to specify the initial state of 10 to the 80th particles is exactly as easy or difficult as specifying the final state of 10 to the 80th particles. That information is conserved. But in quantum mechanics, because of branching, you can imagine that the initial state of the universe is very, very simple. I mean, that's literally what Hartle and Hawking did when they talked about the wave function of the universe. They had a really, really simple initial quantum state for the universe. And then because of branching, that initial simplicity is broken up. And the combination of everything is simple, but the individual routes that are taken by paths are very complicated. Just as I can take, a very simple circular plate, right? A circular piece of wood, and I can cut it using a jigsaw into many different complicated looking shapes. The many different complicated shapes fit together to make something simple. That's exactly what Many Worlds does from a simple initial quantum state of the universe. Gillis15 says, I read about your pending move to Baltimore. Does that mean you will no longer teach at the Santa Fe Institute? Additionally, did you have a chance to tour Los Alamos? If so, what did you think? I'm a native New Mexican, so it would mean the world to me if you answered these. I am moving to Baltimore, but my affiliation with the Santa Fe Institute remains what it was. I will not be teaching there because nobody teaches there. It is not a teaching institution. It is a research institution. My official title there is Fractal Faculty, which means I spend several weeks a year, a couple months a year at Santa Fe. And I'm going to continue to do that. In fact, I'm going to go in August. I will be there. I have once been to Los Alamos to give a talk, but that was a long time ago, and I couldn't really tell you much about it. But I love Santa Fe, love New Mexico. It's a great place to visit. That's one of the reasons why I wanted this affiliation with them. Ken Wolf says, for a while I've been thinking about the utility of near-death experiences as a means of advancement to new levels of sophistication. As an example, our species has experienced... my talking is not very good today. As an example, our species has experienced at least one near-extinction event when we were reduced to a few thousand individuals. As another, the more I read about long-lived civilizations like the Roman civilization, the more their history looks like a series of near-collapse experiences. My question is, have you come across anything in your intellectual pursuits or your personal life that suggests a link between near-death experiences and opportunities for development? Well, short answer, no. If you're talking about actual academic work on this subject, I would recommend not calling what you're referring to near-death experiences, because there's a whole community of people who study near-death experiences in order to prove the existence of life after death. Actual human beings coming close to death and seeing heaven or God or their relatives or whatever. That's what most people think of when you say near-death experience. So I don't think you have that in mind. I mean, of course, there is some general vague feeling that nothing focuses the mind like a hanging, right? Like being in extreme circumstances forces you to think in creative ways, right? If everything is comfortable, if you're near equilibrium, then you can sort of get along making the same slight mistakes that you've been making a long time. And being in dramatic circumstances makes you think. Having said that, I'm not in favor of near collapse experiences, either as a person or as a civilization, in part because of survivorship bias, right? You say things like, or we perceive that, oh, this person or this society or this institution went through a really bad period and came out better the other side. Therefore, really bad periods are good for you. But often, really bad periods lead to you not coming out the other side, right? The risk of not surviving is much more when you're near collapse. So I think that if you were to do a cost-benefit analysis, I would not be in favor of many of frequent near-collapse experiences. That would be my guess. Joshua Hillerup says, I've just had a multi-day power outage here in Canada, where lots of people in my area still don't have power. My question is, what sort of preparation do you have at your home for something like that? Well, my home is changing, as we mentioned above. Here right now, I'm in Los Angeles, where there is a special set of challenges for long-term, I shouldn't say long-term, rare but severe events, right? Like an earthquake or a fire or something like that, mudslides, who knows, power outages. So yeah, like many Los Angeles folks, Southern California folks, we have an earthquake kit with food, basic medical supplies, some simple lighting and masks and warm blankets and things like that. The main problem if we had a severe earthquake here in LA would be a loss of power and water for some period of time. So no one ever has enough water. We do have some water, but everything I've read about these things says you never have enough water because you forget how much water you go through in a day. So we try to have many gallons of water, but probably not enough. So the basics. Moving to Baltimore, of course, Northeast Corridor, it's a different set of worries. Earthquakes, not a major worry, but now you have hurricanes, not to mention just other severe weather events. So we'll be bringing our earthquake kit with us, a lot of overlap between what you need in an earthquake and what you need in a hurricane. We're not looking for places right on the water, so we're hopefully not in danger of flooding, but that will depend on where we live. Who knows? Joe says, if you couldn't get paid to do the various things you do now, what would you do instead to earn a living? Oh, wait, I'm sorry. I wanted to continue with Joshua's question to say one other thing about the emergency preparations, which is that it's a sort of small personal version of a larger societal question about how to prepare for rare but extreme occurrences, right? Everything in our training, our biology, sets us up to survive for things that are likely to happen on our lifespan timescale, right? Things that happen once every 1,000 years are very, very hard to plan for or prepare for. But we should. And I don't have any deep thoughts about that, but it made me think about it when you asked the question. We're very good at preparing for things that happen every week or even every year with high probability. We're not very good at planning for things that happen once every 10 years or even things that would happen once every 100 years, but if they did, they'd be devastating. So I am a believer. I think this was a question that was asked in an earlier AMA, but I am a believer in preparing for those kinds of things and also in appreciating that it's difficult to put precisely the right amount of effort into preparing for something like that. You don't want to be too alarmist about it, but you don't want to ignore it either. Anyway, okay, so Joe's question was, if you couldn't get paid to do the various things you do now, what would you do instead to earn a living? This is a very hard question because the various things I do now are kind of multifaceted, right? So everything I like doing, whether it's teaching or research or writing or speaking or talking to interesting people, these are the things I like to do the most. And my current job, I've managed through hard work. It took me a while, but I've managed to carve out a living where I do a little bit of all of those things. So I'm not sure how to interpret the question. Like if I would have to give up on all of those things, I'd be in trouble. If I'm not allowed to write or speak or teach or do research for a living, it's not a lot. It's not a lot that I'm both competent at and could earn a living doing. I mean, I could imagine, being a different kind of professor, but that's probably not what you have in mind. I could also imagine just being a writer of some sort, even a fiction writer. I have no way of claiming that I'd be any good at that, but because I haven't really done it with any level of seriousness, but that's something I could imagine doing and enjoying. Caliban Carroll asks, I'm sure that's a pseudonym because I know Caliban and he is not a Patreon supporter, believe me. If you were to witness a tremendously unlikely event, say your cat quantum tunneling through a wall, and had no reason to doubt your mental faculties, would you tell others about this experience at the risk of sounding delusional, or would you keep it to yourself? Well, I think that if it were a sufficiently unlikely event, it would be a much more likely explanation that I experienced something, right? Either I was hallucinating or, something wrong with my brain, having a stroke or something like that. There's just a much higher credence that I misunderstood what was happening than literally the cat going through a wall. So I would go to get a checkup or something like that. I would not just hide it and keep it to myself. If it's reproducible, that's an entirely different question, right? Because if something unlikely happens once, that's one thing. If something unlikely happens several times in a row, then it's not really unlikely, is it? Something is making it happen, and that would absolutely be a reason to tell other people about it. Richard Graff says, if I assume there are multiple dark matter particles, what, if anything, would prevent the existence of an entire dark matter universe with structures similar to galaxies, solar systems, planets, and perhaps even life that would still remain undetectable to us? Well, the short answer there is that it's dark, the dark matter. And what we mean by that is, roughly speaking, that it doesn't interact, or it interacts only very, very weakly. If dark matter interacted strongly, even as strongly as ordinary matter does, that's what we don't mean necessarily the strong interactions, but if dark matter interacted with itself, with other dark matter particles, with the same strength as good old ordinary electromagnetism, it would clump and form structures pretty easily. But the point is that we've looked at the universe. We know more or less what the dark matter distribution is, and it's not very clumpy at all. It's exactly what you'd expect for what is essentially a collisionless particle. So there's good reason to think that there's not a lot of interesting interactions in the dark matter sector. So there are two exceptions to that. One is that people have occasionally floated the idea that dark matter particles do occasionally bump into each other, and that helps explain this or that feature of the large-scale structure of galaxies or the satellites around ordinary galaxies and things like that. So far, those ideas, although they're fascinating and would be great if they were true, they haven't quite panned out. There are discrepancies out there between our theoretical models of the formation of structure in the universe and what we observe. So in the podcast episode with Priya Natarajan, we talked about some of those discrepancies. The problem is that mostly, not 100%, but mostly those discrepancies seem to occur in exactly the regimes where it's hard to predict what the standard model would actually imply. So people have suggested changing the physics of dark matter to fix those problems, but often the problems just go away when you look at them more closely. So that's one caveat. The other caveat is, I did once ask myself the scientific version of this question, in particular, could there be an electromagnetic kind of force between the dark matter particles? So when other people do strongly interacting dark matter or whatever, they really mean a short-range force, right? The two dark matter particles come together, scatter inelastically off of each other. Elastically off of each other. They're just like billiard balls, and that sort of exchanges some of their momentum. But could you have a long-range force between the dark matter particles? Something like electromagnetism, right? Let's call it dark electromagnetism. So obviously, for the reasons I just gave, it can't be exactly like electromagnetism because it would clump very easily. But remember, or for that matter, particles would annihilate, like protons and antiprotons would just annihilate. If there were dark particles and dark antiparticles, and they were both charged, you would expect them to annihilate into dark photons. But anyway, there is a free parameter in electromagnetism called the fine structure constant, which has in our universe a value of about 1 over 137. So there's the obvious possibility that you just decrease that number to make the interactions weaker, right? To make the dark electromagnetic strength less noticeable than ordinary electromagnetism. So I did this. I did the science paper with collaborators, Lottie Ackerman, Matthew Buckley, Mark Kamienkowski. Matthew is now faculty at Rutgers, and Mark is now at Johns Hopkins, where I'm going to be joining him. And we'll have an office down the hallway from Mark Kamienkowski. And so we wrote a paper on dark matter and dark radiation, right? Dark electromagnetism. And the fascinating thing that we noticed is that it's easier than you think to get away with having dark electromagnetism, because as long as you make the dark fine structure constant a little bit lower, maybe a factor of 10 smaller than the ordinary fine structure constant, and you make the dark matter particles heavier than ordinary protons and neutrons, the dark matter particles might be 100 or 1,000 times the mass of the proton, then there aren't that many dark matter particles, and they don't interact that strongly with each other. And as a result, they don't really annihilate because they don't bump into each other that often. The annihilation rate becomes fairly small. So you can get away with it. You can get the right relic abundance. It's much like a weakly interacting massive particle, except rather than interact through the weak interactions, it interacts through this new dark electromagnetism, which is a long-range force. The bad news is that long-range forces have their own energy fields, right? The electric field and the magnetic field in our ordinary case. So there is an instability where you can make dark magnetic fields. And dark magnetic fields might dramatically warp the formation of large-scale structure. So we finished the paper by saying that there's this big caveat here that might ruin the whole idea. And we also said at the very end of the paper, once you've done this, so basically what we were proposing was the dark matter equivalent of protons and antiprotons, heavier versions of those. If you also had dark electrons and dark positrons, then you could imagine dark atoms, right? And they could be electrically neutral and stop the instability to make dark magnetic fields. So we mentioned that, and other people have since followed up on that, including David Kaplan, another future colleague of mine, a particle physicist at Johns Hopkins. So they've written papers about dark atoms. And again, interestingly, there is room for that. You can imagine it happening. You gotta really jump through some hoops. It's not the most natural thing in the world, but you can imagine it happening. It has to be more weakly interacting than ordinary matter, or you would have easily seen the dark planets, dark galaxies, etc., which we don't see. But it's a possibility, even if there's no strong motivation for it. It is absolutely something that is interesting and we should look at. Probably not dark life forms or anything like that, because the force has to be fairly weak, but I'm not completely convinced. I'm not allowed to say that, so who knows? Brendan says, I'm always impressed with the vast vocabulary you articulate during your podcast. Was there ever a time you focused on building up your vocabulary specifically, or did it come naturally by reading papers, writing books, talking with people, listening to lectures, etc.? Definitely the latter. I've never tried very hard to build up my vocabulary, but I've always loved words, loved reading, loved talking, and I try to do so in a fairly conscious way. So it's not just that I talk and write, but I think about talking and writing while I do it. So that just tends to very naturally build up your vocabulary. I don't think my vocabulary is all that impressive, honestly, but I appreciate the compliment, Brendan. Thank you. Preston Justice says, if you could learn any other language instantly with native-like proficiency, but only one, which would you choose and why? So I'm going to weasel out. I'm going to give you two different possible answers to this one. If it were purely for reasons of personal pleasure, I think it would be French, because France is the country that I love to visit the most and eat the food at and sit at the cafes and have some coffee and whatever. But I don't speak a word of French, maybe 10 words. I can get around, but probably not enjoy things nearly as much as I would if I were a fluent speaker. If instead of personal pleasure reasons, we were thinking of sort of geopolitical import reasons, then clearly you'd want to learn Mandarin, right? Or some variety of Chinese, because China is an incredibly important country in the world right now, growing ever more important. And it's one that I think that a lot of English speakers don't understand very well, in part because they're not Chinese speakers. I think that would be really good to have more people who actually understood Chinese in the world. There's a lot more Chinese people who understand English than there are Americans who understand Chinese. Louis B. says, I've heard it said that inside the event horizon, time and space switch roles. And this is usually followed by a statement of the form, inside a black hole, you can no more easily avoid traveling to the singularity than out here you can avoid traveling to tomorrow. This second statement gives a reasonably intuitive sense in which a point in space becomes a bit like a point in time. But is there any analogous sense in which time becomes a bit like space? Inside a black hole, can I freely move left and right in time? No, you cannot. And the reason why is because the initial statement, inside the event horizon, time and space switch roles, is complete nonsense. It is entirely hilariously wrong. I know you've heard it before. There's a reason why people say it, and there's sort of more and less respectable reasons why people say it. But the real reason why people are inspired to say it in the first place is because if you start doing the most naive thing outside of a black hole, and so you set up coordinates to try to describe your black hole space-time, right? Mr. Schwarzschild did this, Carl Schwarzschild, when he first invented the Schwarzschild metric for a black hole. So you have x or r, the radial coordinate, theta and phi, r, theta, and phi spherical coordinates, and then you have t, the time coordinate. And then you just naively, without thinking very hard, extend those coordinates inside the horizon of a black hole. What happens is the r coordinate becomes time-like, and the t coordinate becomes space-like. That's a true fact. But it's also a physically completely irrelevant fact. It has absolutely nothing to do with time and space switching roles. It's just a statement about what coordinates we put on time and space. Inside the event horizon, the coordinate that used to be the radial coordinate in space is now the time coordinate. And the coordinate that used to be the time coordinate is now the space coordinate. But there's still space and time. If you were inside the event horizon, you wouldn't even notice that you were inside the event horizon. There would be time and there would be space. And you could move in space in 3 different directions. You move in time only in one, just like always. Now, the statement that the singularity is in the future, not to the left, is completely true. The singularity is in the future, but that just means not that there is some analogy between points in space and points in time. It just means the singularity is not a point in space. It's a moment of time, full stop. Now, the singularity is at r equals 0, but r is a coordinate that gives you the time-like direction. So r equals 0 is a moment in time. It's in your future. It's not at the center of a black hole. That's the truth of it. You can take that to the bank. James Brown says, priority question. I've read your book Something Deeply Hidden twice and listened to it as well. My question is, what is your estimate of the number of times the wave function of the universe has split, or what is its estimated splitting rate? So the short answer is no one has any idea. No one even has any idea whether the question makes sense, because we don't know whether Hilbert space, the space of all possible quantum wave functions, is infinite dimensional or finite dimensional. So forget about real numbers, actual values. We don't even know if it's finite or infinite. If the Hilbert space of the universe is infinite dimensional, then splitting is a continuous process. It's like asking how many numbers are there between 0.1 and 0.2, right? Well, there's an infinite number. There's an infinite number between 0.1 and 0.2, and there's still only 10th as many numbers as there are between 0 and 1, right? Both of those statements are true at the same time. If Hilbert space is infinite dimensional, branching, splitting is just happening all the time, and you can't talk about how many branches there are. It's just a meaningless concept. Now, if it's finite dimensional, which I think is very plausible, then there is some number, which is how often it splits. But that number depends on details about quantum gravity, which we have no idea about, honestly. It doesn't just depend on details of quantum gravity. It depends on details of how we divide up the Hilbert space of the universe into systems and environments and things like that, okay? So it's just not a very well-defined question, no matter how you slice it. But one way or the other, the answer is a lot. It splits very, very often. Let's just put it that way. All right, I'm going to group 2 questions together. One is from Phil, who says, imagine you were handed a program by an artificial intelligence that can perfectly predict any experimental outcome. Not a black box, you're allowed to look at the source code, but the program is so extremely low level or complicated that you can't figure out how anything we see emerges over it. Would you consider physics solved at that point? And then Varun Narasimhachar says, have you tried to reflect on what constitutes an explanatory or satisfactory theory, even just to your own sensibilities? From any given state of science, what factors determine the epistemic directions in which you continue to ask questions? So let me answer Varun's question first, even though it came second. I don't know is the short answer. It's always my favorite answer here at the AMA, is to say that I don't know. It's a you know it when you see it kind of situation. What counts as a good explanation? What counts as a satisfactory theory? However, let me say 2 slightly more detailed things. One is that you can try ahead of time to imagine some criteria for what counts as an explanation or satisfactory or whatever, but nature might not care. okay? So I'm always suspicious of attempts to say this is what counts as an explanation and then demand that nature live up to that. And nature doesn't always work that way. And so the reality of scientific practice is much more a give and take, figure it out as you go kind of thing. We're trying to understand how nature works. We have some theories that are good, some are bad, and we try to make them better. And, that's what it is. And I think that's the right thing that it should be, rather than deciding ahead of time on how things should be. Having said that, the other thing that I wanted to say is that given the progress of science, it is still very interesting to try to be more careful than we are about you know it when you see it in terms of explanatory power. Some theories are more explanatory than others and in different senses than others. So this is a perfectly legitimate thing to try to do within the philosophy of science. So what I'm trying to argue against doing, or at least, raise a red flag about doing, is deciding ahead of time what counts as explanatory. Deciding after the fact why a certain theory is explanatory is a perfectly sensible thing to do. And then to Phil's question, no, I would not count that as explanatory at all, to have a black box and consider physics solved. I've actually mentioned this thought experiment myself before. What that would count as, a black box that could predict any experimental outcome, that's not a theory of the universe. That's just an experiment generator, right? So you can just ask it any question you want, like if I collided two particles together with a certain velocity or whatever, what would come out with what probabilities? You don't need to build particle accelerators anymore. You don't need to have telescopes and so forth. That's what that would be very, very useful for. But an explanation that a theoretical physicist would want is a simple, compact way of compressing all of those outcomes into an understandable theory. And so the box would help you develop that, but it would not count as that all by itself. Vincent Ohm says, should science and physics in particular always strive for explaining the underlying mechanisms and inner workings of the world at different scales? Is that even possible for the quantum world? Or should we just take the equations as a starting point and not ask what is underlying these equations? For instance, the many worlds theory is deduced from the quantum mechanics equations, but it does not explain the mechanism by which the universe splits, or does it? So this is related to the previous two questions, and that's why I put it here, but I didn't want to lump it together because many worlds absolutely does explain the mechanism by which the universe splits. And I knew that was going to, poke my, my pre-existing hot buttons or whatever it is. So I didn't want to lump it in with the other questions. But that's the beauty. That's the whole point of many worlds, is it explains everything. There's no extra stuff. It's just there's a wave function. It evolves according to the Schrodinger equation. When does the universe split? When quantum mechanical systems that are in a superposition become entangled with their environment, aka decoherence, okay? Now, maybe what you mean is, but you haven't explained why the wave function obeys the Schrodinger equation. Sure, you can try to derive the Schrodinger equation from other principles. People talk about that, but you've just invented those other principles. You haven't derived those principles, right? So I just like to say, look, the Schrodinger equation is the equation that the wave function obeys, and I'm not trying to derive it or explain it. That's the bottom. Until we come up with a better theory than quantum mechanics, that is the postulate that we use to construct this theory that we think does such a good job of fitting the data. Marco Tauser says, does many worlds alter the probability you assign to there being other intelligent life forms in the universe? For example, could intelligence occur many times throughout the multiverse, but only once or on one planet in a typical intelligence hosting universe? So yes, I think it does. And actually, maybe I should have lumped this with the previous questions about the emergence of complexity and determinism and randomness, etc., because this is precisely something where there is a difference in how you would think about what happens in the universe if you believed in many worlds versus a single stochastic universe. So remember, for agents who are living in the universe, living in the many worlds interpretation is exactly the same as living in the Copenhagen interpretation or whatever, or hidden variables or what have you, up until the point where such theories are not completely well defined. But you observe one universe with essentially random quantum outcomes. But many worlds says that the whole ensemble of all the branches exists all at one time. And so I could easily imagine I don't know if it's true, but I could easily imagine that the chances of life existing on any one branch of the universe of the wave function are small, maybe even very, very, very small. But there's enough branches that it happens many, many times. This goes back to the idea of sampling the space of possibilities, right? Quantum mechanics and many worlds with its branching structure samples a very diverse space of possibilities, much bigger than any one universe would be able to sample. So exactly because of that, it is completely possible that life is rare in the multiverse, but nevertheless happens many times because there are so many branches. Now I'm going to group a couple questions together once again, a few questions actually, because this was a popular topic after the Judea-Pearl podcast. Oleg Ruvinsky says, in your recent excellent talk with Judea-Pearl, you had an interesting disagreement on entropy. You brought an example of a low entropy state as a triangle of billiard balls set up on a table, and of a high entropy state as all these same balls after they're hit by the cue ball. Judea objected to it by saying that the only difference here is in the eyes of the beholder. We humans understand and recognize triangles, but we don't recognize the pattern created by the cue ball, but that's not a substantial difference. You objected, but I'm not sure I understood your argument as to why a triangle is indeed a low entropy state versus some other random configuration. Okay, that's one question. Matt Rappaport says, in the Judea-Pearl discussion, you discussed the pool table with the balls racked in a triangle, blah, blah, blah. If there are X possible configurations of all the balls, isn't the probability of the triangle configuration and the probability of the dispersed configuration both just 1 over X? I'm not clear on how or why entropy has increased. S.P. Sheridan says, I very much enjoyed the Mindscape interview with Judea-Pearl, but I was surprised that he was not aware of the forward arrow of time being connected with increasing entropy. I was even more perplexed that he disagreed with you on that a person could tell simply by watching a movie on a billiard table if a cue ball breaking a triangle of billiard balls was being run forward or backward in time. And it goes on, but it's basically the same question. Francois Varchon says, is in the biggest ideas in the universe episode on entropy, you mentioned that what we choose to be macroscopically observable is not arbitrary. We cannot see all the atoms as there isn't enough information coming out in the photons. I interpret that as we cannot access all the information from a given macroscopic system. Is this still true for microscopic systems like an atom or a qubit? If not, how does it work? So I hope that that last question, which is a little bit different, you can see how it's relating to the earlier questions. The earlier questions are all about, in the billiard table example, why are we justified in saying that having all the billiard balls queued up in the triangle, in the rack, all nice and neat, is low entropy, and having them scattered around the table is high entropy? And the answer is that we perceive them differently. This is a case where we put a coarse graining on the space of places the billiard balls could be. If all the billiard balls are next to each other, snuggled up together, that's in a different macro state than having all the billiard balls scattered around. And it works in the Boltzmannian sense of thinking about this in terms of entropy. There are fewer ways to arrange the billiard balls so they're all touching each other than there are ways of scattering the billiard balls around the table. So you might object, well, but that's just because I think of it as different and I'm choosing ahead of time to put that particular coarse graining on the set of billiard balls. And the answer is, sure, you are. But guess what? Doing so gives you a handle on what's happening because the billiard table is not a closed system. If you were to just walk into a room with a pool table and see that all the balls had been are sitting on the pool table in a neat little triangular array, you would know that it is not just a random configuration of billiard balls, even though that configuration is just as likely as any other configuration. There is something special about that makes you think, aha, someone racked the billiard balls, right? And the same thing is true for much more realistic systems. I mean, of course, the billiard table is realistic. There are billiard tables in the world, but it's not a great example of entropy because there's not that many balls, right? So you can't quite see the large N limit here when there's only, whatever it is, 15 billiard balls on the table, as opposed to like 10 to the 20 or 10 to the 30 particles in some macroscopic collection of matter. So in the real world, where we're talking about thermodynamics and real world systems, The difference between having all of the air molecules in 1 cubic centimeter in the corner of a room versus having all the air molecules dispersed throughout the room is dramatic and very, very noticeable. And precisely because the universe began in a very low entropy state, we nevertheless do find stuff in low entropy configurations in exactly this sense of the coarse graining that you and I choose to put on it. And that helps us understand the world, because we can talk about that and then understand why you see ice cubes melt and you don't see ice cubes unmelt. That's a fact about the world that we observe, and we understand it in terms of these coarse grainings that we put on the world. Now, as Francois alludes to, there are reasons why we choose some coarse grainings and not others. And it's more clear in the case of big thermodynamic systems than it is in the case of the billiard balls, because you coarse grain based on what you see. You can see the ink in the water. You can see the ice cube in the glass of water, right? You can see its macroscopic configuration. You can't see all the atoms. And so there's an immediate relationship between our physical interaction with the system and how we choose to coarse grain it. Now, you could perfectly well apply that to the billiard ball example, because we have ways of thinking about the billiard balls and communicating about them. If you say to someone, the billiard balls are all racked and ready to be broken at the beginning of the game, you instantly know more or less precisely the position of the billiard balls. I mean, some people might actually arrange them within the triangle slightly differently, but up to that rearranging, you know exactly what the billiard balls are doing. Whereas if someone says the billiard balls have been broken, they're scattered across the table, you don't know the exact positions of all the balls. There are many, many microstates that correspond to that description. So there's a real physical difference and a reason why we choose to coarse grain in that way, even though you could coarse grain in other ways. You could invent some weird set of locations on the table and say that I will call it low entropy if the billiard balls are in exactly those locations, and high entropy if they're anywhere else. You could do that. It would be useless because you're never going to see the billiard balls in those locations. There are good physical reasons why we choose the coarse grainings that we do. Okay, Sandro Stuckey says, I've seen many explanations of Heisenberg's uncertainty principle that go something like this. To measure the position of a particle more precisely, we want higher resolution, so we need to use higher frequency photons, which affect the velocity of a particle more because they have higher energy. Then there's a derivation of the relationship between position and momentum via the relationship of frequency and energy. I know that the uncertainty principle is much more general than that, and that it is fundamental in quantum physics, so is the above explanation wrong, or is it correct but just an illustration? Well, it is correct, it is not wrong, but it is not an explanation of the uncertainty principle. It is one way of thinking about one of the consequences of the uncertainty principle. But the uncertainty principle itself does not make any reference to measurements or observations, certainly doesn't make any reference at all to the mechanism by which we measure things, okay? The uncertainty principle is just a statement about what possible quantum states exist, not a statement about what happens when we measure them. As a consequence of the uncertainty principle and the nature of quantum mechanics, you can derive things like, if you were to measure the variables like position and momentum, there is no quantum state for which you could measure them exactly, or you could predict exactly what you're going to get for both such variables, position and momentum. But even if you chose never to measure it, it would still be true that expressed as a superposition of positions or momenta, there are no quantum states that are exactly localized in position and momentum simultaneously. And in fact, the more localized any one particular state is with respect to position, the less localized it is with respect to momentum, and vice versa. That's the uncertainty principle. And it's really just a matter of choosing different coordinates, right? I mean, the explanation that I use in Something Deeply Hidden, and probably elsewhere, is just think about a two-dimensional plane, right, with x and y coordinates. And I can draw a vector that points 100% in the x direction, or 100% in the y direction. Nothing stops me from doing that. So these would be states of definite x and y. But then I can also draw coordinates on that plane that are rotated 45 degrees with respect to the original ones, right? X prime and y prime. I can also draw vectors that are completely oriented on the x prime direction or the y prime direction. What I can't do is draw a vector that is 100% oriented on both the x and the x prime directions at the same time, because they're rotated with respect to each other. That is the uncertainty principle. Position and momentum are just two different coordinate systems in Hilbert space, and you cannot localize in them both simultaneously. Paul Kent says, which bass guitar model do you own? And when you do eventually find the time, which other music genres or notable bass players will you look to for inspiration or technique guidance? Well, I own an Ibanez. That is the bass that I have sitting behind me right now. And as I mentioned before, I have not been playing it very much. I love a lot of bass players in all sorts of different genres, but I can't really, in good conscience, say that I'm looking to them for inspiration since they are so far away from me. I'm still learning how to play scales and things like that, right? My favorite rock bass players are Chris Squire, Jack Bruce, Geddy Lee, John Entwistle is one of my absolute favorites. There's also jazz bass players, Jaco Pastorius and so forth. Charles Mingus is absolutely amazing. And there's a million session players or lesser known people who have amazing technique who, you don't become famous for one reason or another. So I don't have, specific favorites in that. No, I do have favorites. I do not have people I'm trying to emulate. Let's put it that way. Flying Waffle. Oh, I remember what I wanted to do. I wanted to tell you the time I got to appear on stage with Flea of the Red Hot Chili Peppers. This is not a spoiler alert, I don't think, but Flea, in a very adorable circumstance, is one of the actors on the new Obi-Wan Kenobi series. I'm not sure if that's a well-known fact, but again, I'm not really spoiling anything. So I recognized him as soon as I saw him. He lives in LA like many working musicians do, and I live in LA. And there was, I'm not so sure exists, but there was a program called Musique in Pasadena, which would put on quirky, experimental musical performances for audiences. And this was years ago. And the gimmick in this case was to have a rock bass player, a classical cello player, and a theoretical physicist get up on stage and take turns interacting with each other in different ways. So it was me, Flea of the Red Hot Chili Peppers, and Matt Heimovitz, who is a cellist. And, it was one of the very few times in my career of getting on stage that I really wished I had just not gotten on stage at all. Not because it wasn't fun for me, but because the real highlight of this event was Matt Heimovitz, the classical cello player, and Flea, the rock bass player, just improvising on stage together. Like every second that I was up there talking was a waste of this precious opportunity, honestly. But I did, I got up and told a little story about Galileo with Flea improvising on the bass behind me, and that was a lot of fun. I don't think that there are any recordings of this event, but I swear I'm not lying to you about it. Flea is pretty awesome also. He's a great bass player. Okay, Flying Waffle says, you mentioned that an electron and a positron can be assembled into positronium, something similar to a hydrogen atom. But then in what situations does matter and antimatter actually annihilate? So positronium annihilates. You can put positrons and electrons together in an orbit, but they don't last very long. They do annihilate for exactly this reason. Positrons and electrons combine to make a couple of photons. But it does take some time. So you calculate. This is, something that if you're insufficiently lucky, you might be assigned as a homework problem in a quantum field theory course. Imagine that you are in the ground state of positronium. What is the lifetime? That is to say, what is the average number of seconds before they annihilate? And it's a non-zero number, but it's a very short number. Positronium doesn't last very long. The Neuropean says, you occasionally put ads into the free podcast episodes. Could you give us some background as to how this came about? Do you just select from individual offers you get in your inbox, or do you reach out to brands you like? Is there a lot of freedom in how you phrase the ad? Are you happy with adding the occasional ad so far, or does it not make out that much of an impact compared to Patreon? So actually, yeah, the Patreon itself came about at the same time as the ads. So once the podcast came into existence, I was reached out to by an agent who said, I would like to sell your podcast to a podcast network who will put ads on it and we can all make money. And that happened, and I joined Wondery. Wondery is my podcast network. Wondery mostly does narrative kinds of podcasts that they will eventually work into TV shows. So I am not that. There's never going to be a Mindscape TV show. But basically what Wondery does is sell ads that we put in the podcast. And once that started, I thought it would always be a good idea to allow listeners, if they wanted to have ad-free versions of the podcast. So that's why I created the Patreon in the first place. In the early days of the podcast, there wasn't any. And so the Patreon came into existence as a way to get the podcast without ads. And it's taken on a life of its own for very good reasons, which is wonderful. I still don't make as much cash from the Patreon as I do from selling the ads. So the ads are a bigger income stream than the Patreon is. They're comparable, same order of magnitude, but the ads are definitely bigger. I'm generally pretty happy with it. One of the things about the contract that I have with Wondery is I can refuse any ads, any advertiser that I want. And you'd be shocked at how many advertisers I refuse to advertise. Not because they're evil or bad or whatever, but there's a huge number of companies that want to advertise health products, okay? So whether it's, diet supplements or whatever, and I just can't, as a scientist, be seen to be endorsing these if I don't understand them, right? And I don't understand any health products whatsoever, as at a professional level. So that's a huge part of the podcast ad ecosystem, and I just don't participate in it at all. But that's okay. I'd rather only have ads for things that I believe in. So even things that are not health endorsed, or health related, which I think I can, if it's here is a suitcase company, okay, I will, even if I'm not familiar with the suitcase, I will check out online, are they reputable, do they get good reviews, things like that, and if they seem to be a scam or not reputable, then I won't do it, and I've turned down advertisers for that reason also. And finally, when it comes to the script, they generally give you a script and you read it. In fact, they would like it if I improvised more. If, I acted like this was just my own words. But, there's not a lot of time in the day. And so I'm very happy if they give me a script just to read the script. So I look for some sort of compromise there, because typically they ask that you experience the product. So like when I talk about kitty litter or coffee or whatever on the podcast, I have drunk that coffee. I have given that kitty litter to put in the cat box for Ariel and Caliban. I've tried it out, and I can say in good conscience that it is worth doing. So I do have some personal experience with essentially all these things that I am advertising. So I'm perfectly happy with the advertising. If people don't want it, they can join Patreon, right? And nevertheless, a huge fraction of the people who listen to the podcast listen to the ad version. They do not come onto Patreon, so that's the choice they're making, which is great. Anonymous says, there are good ways to carve reality into objects, like Jupiter and Air Force One, and bad ways, like an object, parts of Jupiter and bits of Air Force One. Are there physicsy ways to think about how I choose a good ontology? Like, am I using labels to minimize the Lyapunov exponent for my measurements, or maximizing information conservation, or something mathy like that? Well, this is a great question and a crucially important question, right? This is basically the question of emergence. How do you carve things that are made of atoms or quantum fields or whatever into large macroscopic objects in useful ways? And I think everyone agrees roughly on the point of this kind of carving, which is that you carve nature into ways such that when all the information you have is information about the chunks into which you carved it, you are left with the ability to say something interesting, to make a prediction for the future, or to understand what's going to happen next, or anything like that. So you look for, the finest grained ways you can chop things up and yet maintain some ability to characterize the system in a small number of bits while yet predicting what's going to happen next, maybe up to some probabilities or something like that. But that's the general idea. However, taking this general rough idea and making it precise turns out to be really hard, especially when there's incomplete information about the underlying system. So like one obvious example that I always like to remember, because it's so obvious people can actually understand it, is the center of mass of a celestial object, right? We can track the motion of the moon and the earth and the solar system without tracking the positions of all of their atoms and molecules. And that's still deterministic, right? Not only do you know what the earth will do, but you know it deterministically. And Isaac Newton was able to do this, and we can predict eclipses and things like that far, far in the future. Very often, that's not going to be the case. If the higher level systems are something like a person, or for that matter, a volcano or a hurricane, maybe the best we can do is some probabilistic predictions. And then you get into a whole different set of questions about how do you minimize uncertainties given these probabilities, etc. So I chose this question for answering because I literally am doing this as a research program. And this is not something I've made a lot of progress on, but I'm very, very interested in reading what other people have done and trying to make my own little contributions to it. What is the general theory of what emerges from what? How do you carve microscopic things into macroscopic things? I think that there is no general answer to that I know of right now. People have suggested things. I mean, we did a whole podcast with Anil Seth on more or less exactly that, but only in a pretty restricted domain of possibility. So I think the general questions are still very, very open. Justin Wolcott says, do you think there's any benefit for the average person to spend more than, say, 30 minutes a week on current events news, like CNN, Fox News, MSNBC, etc.? The news this week is particularly sad in America. I feel like I can't change anything other than by voting, which I would have done even if I didn't watch 3 hours of CNN and New York Times every day. So why not save some time and do something else? I think this is actually a very important and interesting question. It's a subtle one. It's a difficult one because it's easy to say that all the citizens who do their voting should be well informed, etc. But you have to be a little bit more specific about to what end you're being informed. One little footnote to the question is there are things you can do other than voting. You can convince other people to vote, right? You can persuade other people. You can lobby your existing representatives, and those things also have an effect. So it's not just you particularly voting. And when those things happen, when you're talking to other people around you or when you're lobbying your representatives, maybe it does matter that you're hyper informed about a particular issue. You know, you come off as more credible and knowledgeable. However, I get the focus of the question because we're in a very polarized society right now. You know, go back to the podcast we did with Will Wilkinson and Ezra Klein, analyzing just the fact that the polarization doesn't mean that people are different from each other. It means that their differences align, so that in the political situation in the United States right now, people who agree or disagree about a certain issue are more likely than ever before to agree and disagree about other issues. And that makes it harder to find overlap, but easier to realize, well, this candidate is closer to me than this other candidate, right? And so I think that we're in a situation right now where you don't need to be hyper educated about current events to figure out that one candidate is closer to your interest than another one is, for better or for worse, right? So I do think that there is a sort of pragmatic kind of, at least in this current moment, argument to say you need to be up enough on current events that you can pick, are you Republican or a Democrat, roughly speaking? And that's just not that hard. And once that happens, you know who to vote for, and the extra information is maybe interesting and so forth, but doesn't actually affect who you vote for. So again, I would put the reasons to become better informed, not these days as feeding into who you vote for, because that's kind of just too obvious in our present system, unless you're really right in between, which is a rare but existent species. But there's also other things. There's talking about the issues, there's thinking them through, talking with your representatives, writing letters, writing emails, joining campaigns, deciding when something is significant enough that you would march or donate money to an interest group or whatever. So it's for those reasons, not for voting reasons, that I do think it is worthwhile becoming informed about what's going on. Casey Mahone says, have you ever been through a bad breakup and how did you get over it? Yeah, I have. I'd like to think that almost everyone has, right? Once you reach a certain age, some people are lucky they marry their high school sweetheart and it works out for their lives. Most people in the modern world aren't like that. There are breakups, and sometimes the breakups are bad. Yeah, that happens. And bad doesn't mean, you're throwing plates at each other or whatever. It might just mean that it's sad that you're breaking up for whatever reason. I mean, maybe it's sad for one person and not sad for the other person. I don't have any great advice. I don't think there's any magic bullet here through getting over those things. The only kind of marginally relevant factoid I will pass along is I once heard a talk by Philip Zimbardo, who is a psychologist who's kind of infamous for the Stanford prison experiment. But later in life, he's been thinking about the psychology of people's attitude towards time. And, he talked actually about the marshmallow experiment, the marshmallow test, which was not his. He was not the one. It was Walter Mischel who did that first. But Zimbardo was trying to argue that one of the things that is revealed by the marshmallow test, where you're given two marshmallows. Sorry, what is it? You're given one marshmallow. You're a kid. You're like 8 years old or whatever. And you're told either you eat the marshmallow now when I leave the room, or if you don't eat it, I will give you two marshmallows. And the point is supposed to be that this reveals an orientation of the person toward time. There are future-oriented people, present-oriented people, and past-oriented people, okay? And of course, this is a wild exaggeration, but there is supposed to be some effect there. There's supposed to be some continuum on which people lie. And Zimbardo's claim is that you can test for this. Are people more future-oriented, past-oriented, present-oriented? And it's a more robust psychological characterization than almost any other one you can find. It's a very basic, fundamental feature of who people are. And to that extent, I am a future-oriented person. This helps me out getting over the bad breakups. To get back to Casey's question, I really do care about what comes next. The bad breakups for me are the ones where I can't get over thinking that maybe we'll get back together, right? If it just is over, then I have relatively little trouble moving on to the next thing. And it's not that being future-oriented is better intrinsically or more ethical or moral or self-actualized or whatever than being past or present-oriented. It's just that it gives you a slightly different perspective that I think helps you get over dwelling on the bad things that have happened. You're always getting excited or depressed, depending on the situation, about what is going to happen next. So maybe the teensy bit of advice would be to sort of cultivate a future-oriented perspective in those situations. Think about what's going to happen, what your next thing will be, how to make that come about. What are the things you can do to affect the future? That's something that I've always been very fortunate that I have had as an attitude, which is I don't want to just say things are bad. I want to ask, how can I make them better? If we're just sitting around talking about how terrible things are, I'm completely uninterested. What are the things we can do to change it? That's what I want to know. And I sort of drifted off into more global issues, but I think that works for romantic entanglements as well. Noble Gas says, your conversation with Nick Lane and others offers hope that we will soon have a plausible understanding of the origins of life on Earth. Your conversation with Anil Seth and others offers hope that we will at some point understand the origins and emergence of phenomenal consciousness. I see no hope for potentially understanding the origin of the universe. You've suggested that maybe we just have to accept a list of brute facts for that question. Given the progress we've made on other hard questions, doesn't that seem like a cop-out? Do you truly not think we will be able to do better than a list of brute facts to truly understand the origin of our universe? Well, no, I'm someone who definitely believes we are making progress on understanding the origin of the universe. That's absolutely something to do. And simultaneously, there will be involved in that at some point a list of brute facts, just like for our understanding of life or consciousness. You try to explain the origin of life, but you take as brute facts all of chemistry, right? You don't need to say, well, until I understand the periodic table of the elements, I don't understand the origin of life. There's some facts you just take as given. And you might say, well, that's left for physics or chemistry to explain, right? But that's going to bottom out somewhere. There is more than one possible world. There's more than one way the world could have been. And in some sense, there might be something special about our world. But even if there is something special about our world, it doesn't explain why the world is that way. It's just a fact about our world. And, we're in our everyday lives, we often don't want to just accept brute facts. We think that there's always a deeper explanation. But you can't extend that kind of reasoning about our everyday lives to big fundamental questions about the universe. I am someone who literally believes it is impossible to imagine that there aren't brute facts about the universe, precisely because there are other ways things could have been. And there's just a fact that things are this way rather than other way. That doesn't mean we have to just stop thinking about it, because we're not sure what those brute facts are. We can always try to hope for a better explanation than what we currently have. That's what we do as scientists and philosophers. Patricia Paulson says, I get the impression you aren't thrilled about loop quantum gravity. I'm just a math-deficient layperson, but it just seems to make sense. A smallest distance doesn't seem any different than discrete jumps in an electron's orbit or energy, or strings only vibrating in specified ways with nothing in between. Wouldn't that be a type of symmetry? So while it is just my math-stupid self saying it makes sense, what are your objections, or what are the objections others have? Is it all in the math? Well, I think that these are perfectly good reasons, motivations to think about loop quantum gravity. This is how science works, this is how physics works. You have an idea, you develop that idea into a rigorous theory, and then you compare that to how the world works in direct or indirect ways. So yeah, you can say, well, maybe there's sort of a discreteness in space-time. It's a very, very natural thing to say. But that's not the end of your project. That's the beginning. You say, okay, what does that mean mathematically? What predictions does it make, and so forth? Does the theory make internal sense? Is it coherent? Is it consistent? And things like that. And I think that, for all those questions, loop quantum gravity has just not worked. There you go. I'm not against the idea of trying it. It was a great thing to try. But it's clearly missing some important aspects of how gravity works in the real world. The most obvious one are the non-local aspects of gravity, the aspects that show up in holography and complementarity and black hole information. These are all things that were understood first outside the context of loop quantum gravity. There's no puzzle or feature that seems to be universal about gravity, as far as I know, that was first brought up or discovered in the context of loop quantum gravity. They've discovered things that are supposedly true in the context of their theory, which is great. But I think that the arguments for things like holography are robust enough that they should be true in any theory of quantum gravity. And this idea that you just put degrees of freedom at local positions in space is exactly not holographic. That's exactly not, set up to be compatible with that fact about the gravitational universe. So, maybe they just haven't gotten there yet. It's always possible, but that's just true, again, for all of physics. When there's lots of different theories on the floor and you need to pick which one you're looking at, all of them are possible. Maybe they could be developed with smarter people doing really good work into something that fits the data, but you have to choose what seems more promising than others. And it seems to me that the basic first moves of loop quantum gravity are not the moves to make, as far as we understand in other things that we've learned about quantum gravity more generally. Michael Lesniak says, I'm really interested to hear your take on the movie Tenet and how it portrays entropy as a means to time travel. Does it hold together, and does having to breathe backward air even make any sense? So the short answer is no, it makes no sense at all. It's completely movie fiction. It's fantasy. It's not science fiction. It's sort of inspired by various scientific ideas about entropy and the arrow of time and things like that, but there's no real science to what happens in Tenet is the short answer. And that's okay. I haven't seen the movie in a while, so I can't tell you details, but I can enjoy the movie as a movie. It's as realistic as, the Fast and Furious franchise in many ways. There's a lot of things that are not very realistic there, but still enjoy the movie. That's okay. Moshe Fader says, I recently completed a house hunt that took roughly a year, so I'm curious about what sort of house you and Jennifer are shopping for in the Baltimore area. Do you have a target size in mind? Do you prefer modern or traditional architecture? Yeah, well, these are all very relevant questions to my brain right now. I'm thinking about them every single day. We still have not found a house that we've settled down on, but with the internet these days, it's kind of amazing. We can do a lot of house hunting from California, even if we're hunting for houses in Baltimore. They put a lot of information online, which is very, very helpful. But there's nothing quite like stepping into the house and, feeling it and smelling it and looking at the sight lines and imagining where your sofa will be and all those questions. So the nice thing about Baltimore is that real estate is way more affordable than it is in Los Angeles. Los Angeles is cheaper than a couple of other cities in the United States, maybe New York, San Francisco, Boston, but still pretty expensive by any ordinary stretch of the imagination. So when we sell our house here, we will be able to buy a house that is much larger in Baltimore. Now, there's two sort of basic modes. You can get kind of a townhouse downtown, maybe close to the waterfront or something like that. Those are very, very nice, very beautiful. There's a big selection. And there are also, big older houses, a lot of 100-year-old houses. There's sort of a building boom in Baltimore 100 years ago, especially near the campus, near Hopkins. And so I think we're leaning in the latter direction. I mean, I think that if we had infinite money and could pick houses anywhere in the world and build our own from scratch, we would go very modern in terms of architecture, very contemporary. But given what exists, I think there are beautiful colonials that are, a 15-minute walk from campus that are surrounded by leafy, nice neighborhoods that, would be great with lots of square feet. So probably something like that. Jennifer is very energized to, renovate a kitchen, tear out some floors and replace them with better flooring, things like that. So that's just sounds exhausting to me, but I think that we'll work out something. It's both exciting and nerve-wracking at the same time, right? It's a big thing. We expect to live there for a long number of years. And so you want to choose right from the start. We'll probably move there into an apartment for a little while, since we haven't found the perfect place yet, and then keep hunting for houses in the months to come. Rue Phillips says, I've heard you allude to the fact that you are now working on quantum gravity research. Did I hear you correctly? What are you hoping to accomplish in that field in the near term, the next 2 years? So, yeah, I am doing quantum gravity. I've even there's a whole solo podcast on it from early days about the emergence of space-time from quantum mechanics, which is a kind of quantum gravity. And, by the way, you don't need to wonder about these things. You can just look for any scientist, what they're working on, by looking at what papers they've written. You can go to Google Scholar, for example. There's various other more specialized lists of publications that you can find online, but Google Scholar has a pretty good coverage overall in all fields. It's a little bit difficult because, there are other people named Sean Carroll, like previous Mindscape guests who are biologists and so forth. But if you put in the middle initial, you can find my publications very easily and just, search by date, sort by date, and then you'll find out what I've been working on lately. What do I hope to accomplish in the next 2 years is almost impossible to answer because in theoretical physics, you do what can be done, right? So there are many things I would like to do, but within this idea that we have of starting with a finite dimensional quantum system and seeing how space-time can emerge, there's a number of obvious questions to ask about the emergence of Lorentz invariance, the emergence of quantum fields, whether or not the metric that you can define using entanglement is physically the metric that is felt by propagating particles and fields in that geometry, things like that. So there's a whole bunch of things. The particular angle I have is very new and immature compared to something like loop quantum gravity or string theory or causal set theory or whatever. So many of the very basic questions haven't been answered, which always means that as I always want to emphasize, the whole thing could crash and burn very quickly. It could just not work. You don't know. But we're trying. I think that it's optimistic that we're going to make some progress. Progress has definitely been slowed by the fact that I'm moving from Caltech to Hopkins, and therefore at the moment I have no students or postdocs working with me. So my publication rate is going to be smaller this year and next year, but I'm hoping to ramp that back up once I get to Baltimore. Rob Patro says, you recently had a nice thread on Twitter about determinism and free will. It spurred a nice follow-up thread on what it means for a system to be deterministic. My question is our best model of the universe deterministic despite quantum mechanics? Perhaps I don't know which of the many worlds holds my future, but it would seem the entire tree or directed acyclic graph of the universe is entirely determined, including the probability amplitudes of each branch. So there's two senses here. One is that in many worlds, the wave function of the universe it evolves deterministically, as we've already said. That is true. But that's irrelevant to observers. You don't care about that because you only live on one branch at a time, okay? So to you, there's a probability distribution. And that doesn't count as being deterministic. So if all you can predict about the future are the probabilities of certain events, that's great. That's a huge accomplishment scientifically. But it does not count as saying that the world is deterministic. Just because the probability distribution evolves deterministically doesn't mean the world does. So once you take quantum mechanics into account, I think that the right thing to say is that our world, the world that we observe, is just not deterministic for all intents and purposes. Paul Hess says, in your interview with Sean B. Carroll, just mentioned, the idea was raised that the mutation rate of organisms is in theory adjustable. If you could adjust the human mutation rate, would you increase it greatly in response to the much more rapid changes in climate and technology we are facing, or reduce it greatly to provide a stable base for adaptation using technology our race is going through, non-biological evolution? Particularly, my individual self would not mess with the human mutation rate. And that's because, it's more or less, not precisely, because there are things that we can't control, but biology has tuned that mutation rate to be just about right. If the mutation rate is larger, remember, most mutations are bad, okay? Most mutations kill you, or at least harm you in some way, because we're pretty close to optimized given the general features that we have as biological organisms. Not just human beings, but all mature species are like that. If you slow it down, the mutation rate, then it is harder to make even more progress biologically. So it's probably about right. Now, you are pointing out correctly that we are living in a time when our conditions are changing more rapidly than usual. So this mutation rate that has been selected or controlled by natural selection is meant for a time when changes are slower. That's true. But like you also say, there are ways that we can adapt to our changing circumstances that are not through changing our genomes, through non-biological or technological changes. So I think that I would be cautious in this particular way. There's also the question of individual not rights, but individual welfare versus group welfare, right? If you increase the mutation rate in human beings by any noticeable amount, you would get a lot more sick babies, and those individuals would suffer even if occasionally some of them would adapt in a positive way. And so the question is, how many people do you want to suffer just to make some that are doing better? And I'm not in favor of really increasing that number by a great amount. Igor Parshkin says, my question is about the equality sign in mathematics. I always imagined to myself it means that two sides of the equation are completely equivalent, i.e. F equals ma is saying that the force is acceleration just with a proportionality constant. They are the same thing, just in different words. But I recently realized that this does not always hold. For example, the Schrödinger equation says h psi equals E psi. It doesn't mean that using an operator is the same thing as energy. So in short, what does equality mean in math? So I think there's a few things going on that I need to clear up here. One is that the Schrödinger equation does not say h psi equals E psi. That is the time-independent Schrödinger equation, which is just a special case of the real Schrödinger equation. The real Schrödinger equation says h psi equals I d by dt psi, the time derivative of psi. Okay, so that's a much more general thing from which you can derive the equation that you wrote down. The other thing is that you're asking about what equality means in math, but your examples are all what equality means in physics, which are different things. Equality doesn't mean identity. It doesn't mean that two things are defined to be the same thing. So you give F equals ma as an example, but think about the inverse square law for gravity, right? The force of gravity is g, Newton's constant, times the mass of one, the mass of the other, divided by r squared. That's not supposed to be telling you that the force is that 1 over r squared thing times the masses. It's numerically equal to it, but it's conceptually a different thing. That's what's going on in the Schrödinger equation, and it's even much more obvious in Einstein's equation for general relativity. In general relativity, you have r mu nu minus 1/2 r g mu nu on the left-hand side, and even if you don't know what those symbols mean, what they're telling you is the curvature of space-time. Okay, and on the right-hand side, you have 8 pi g t mu nu, which is telling you the energy and momentum in space-time. Conceptually, two completely different things. The equation is just telling you they are numerically equal in solutions to Einstein's equations. In other words, in classical spacetimes in the real world. So that's always the way you should think about it in physics. In physics, an equation is telling you that two differently defined quantities are numerically equal to each other. In math, it can mean lots of different things because math is not about a substance, right? Math is not about an individual domain of applicability. Math is more general than that. Math is about syntax more than semantics, if you want to put it that way. It's about the symbols more than their meaning. The same symbols can mean different things, but 2 plus 2 equals 4, whether the 2 things and the 4 things are apples or oranges or whatever, okay? So it's a slightly different meaning in math and in physics, but in neither case is equality supposed to mean these two things are the same concepts. It just means they're numerically equal. Alejandro del Rincon says, according to general relativity, mass and energy warp spacetime. I'm not sure this is a sensible question, but why? Is there an interaction between the two or some sort of friction that causes the warping? Well, this is dangerously close to the kind of question that the answer is, it just is that way, right? I mean, that's the equation. That's what the theory says. The theory postulates that mass and energy warp space-time. But as I said above, sometimes you can kind of try to derive equations like that through some other principles. But you're just replacing one set of postulates for another. So you're welcome to just postulate Einstein's equation of general relativity and say that this is one of the postulates of the theory. Nothing wrong with that. In that case, it just is true. But you can also derive it from some other set of postulates, for example, the principle of least action. The principle of least action says that along physical trajectories, if you imagine the space of all possible trajectories for a system, which in general relativity means the space of all possible space-times between some initial configuration and some final configuration. And then you can calculate a number called the action for all of those trajectories or all of those space-times. And what you find is that the one that is actually a solution to the equation the motion is the one that has the minimum value of the action. And this makes perfect sense when it's a simple system like a ball rolling down a hill, where the action is an integral over time of the kinetic energy minus the potential energy. So it's not the total energy, which is just constant along the trajectory, but it's basically some kind of competition between kinetic energy and potential energy. So you're trying to minimize kinetic energy minus potential energy along a path between 2 points. And you might say, well, good. So just minimize the potential energy is always positive and the kinetic energy is always positive by themselves. Let's say that you've set things up that way. And you want to minimize kinetic minus potential. That means go to very large values of the potential and very small values of the kinetic energy, right? The problem is you have a boundary condition. You just start somewhere and end somewhere. And you set up your initial conditions. So you start at some place at some time and you end at some other place at some other time. And subject to those constraints, you want to minimize the kinetic energy minus the potential energy, which sort of means, roughly speaking, you go as slow as you can to get to where you want to go in the right amount of time. You don't just speed really fast and get there and sit there. That's not the solution to the equations of motion. So in general relativity, translating those words into the context of curved spacetime says that there's a balance, there's a trade-off. Just like versus kinetic and potential energy, there's a balance or a trade-off between the amount of stuff in the universe and the curvature of spacetime. So spacetime curves as little as it can to adapt to the amount of energy that it has in it, to minimize the action there. In some sense, that's no better than just postulating the final answer because, well, why is that action the one that is minimized by these trajectories, right? But, this is how the world works. The world is full of fields like the gravitational field. They all move and vibrate and oscillate, and they all interact with each other in one way or another. The stuff in the universe that makes up matter interacts with the stuff that makes up space-time, and that gives us the equation that we have at the end of the day. Abdi Ayao says, with all the craziness and madness going on in the world right now, do you think one day in the future, hopefully soon, the James Webb Space Telescope will find something that blows people's minds and brings humanity closer for the purpose of advancing humanity's civilization. So there's there's a good question, two levels of answer here. One is the Webb Space Telescope going to find amazing things? And the other is, will that bring humanity closer together? In the latter question, honestly, I don't think so by any reasonable amount. The kinds of things that historically have ended wars or induced world peace are not scientific discoveries, as far as I can tell. They do play some role. Science is part of the legacy of all of humanity. It doesn't belong to any one person or country or anything like that. And everyone can be impressed and wonder at a great scientific discovery. But empirically, the effect of that on human behavior is pretty small. The other is, will the Webb Space Telescope make these world-shattering discoveries? I don't know. It will certainly make big discoveries because they're sort of targets. The thing about building a new telescope or a new scientific experiment is you can't predict what you're going to see. Otherwise, if you knew what you were going to see, you wouldn't build it. You would save the money. So you're looking into the unknown a little bit, and that's part of the excitement. However, you can't get money from NASA or Congress without giving good expectations that you're going to see something interesting. So for the Webb, there's two obvious targets here. One is galaxies in the early universe, the very early formation of stars and galaxies, right? Because the Webb is focused on infrared radiation. So unlike the Hubble Space Telescope, which was looking at visible light, JWST is looking at longer wavelengths. And one of the reasons why that's interesting is because if you have a galaxy that is very early, that is just like our galaxy, mostly giving off radiation in the visible spectrum, once it gets to us, it's redshifted to the infrared. So you have optimized yourself to look further back in time if you build an infrared telescope like JWST. So that's interesting. But it'll mostly be interesting to astronomers and cosmologists, right? We know that galaxies exist. Understanding how they are assembled and understanding how stars light up is very, very interesting, but it won't be a complete world-shattering shock. The other thing that JWST that I know about that it's going to look for are exoplanets and features of exoplanets, planets around other star systems. So that is very exciting. We know less in some sense about exoplanets than we know about other galaxies. We found thousands of exoplanets and trillions of galaxies. Or millions of galaxies anyway that we've actually found. So that has, for obvious reasons that I don't need to delineate here, the prospect of being really, really exciting if everything goes well. Probably we'll just get an inventory of exoplanets, right? But we could get more interesting things as well. That's something to hold out hope for. Matt Lane says, do we need more academics to get involved in and run for political office? What could we do to support a higher level of education and discourse in our politics? Well, I think that there are some academics who would be great running for political office, and some have successfully. Many academics would be terrible at politics. I don't think there's any intrinsic connection between being an academic and being good at politics. In the modern world, for better or for worse, the job of being a politician, a lot of it is either fundraising or negotiating with your fellow politicians, right? Those are the things. It's not about just having the right policy prescriptions. It's about getting things done with those policy prescriptions. And I think that a lot of people, fall in love with this or that politician because they say the right things. But personally, I want to know what they've gotten done. What legislation have they gotten passed, or what reforms have they accomplished, or whatever. That's another level of trickiness. And again, one that academics are not themselves especially good at. But this is related to the second half of your question is, should we have a higher level of education and discourse? That's an easier one. Yes, I think that we should. In many ways, our current political system here in the United States, and I think also elsewhere, it's a little weird. Someone was pointing out the ages of the people who wrote the Constitution of the United States. A lot of the people, both at the Continental Congress that did the Declaration of Independence, and then also at the when they wrote the Constitution, they were in their 20s and 30s, a lot of them, and a few were in their 40s. Almost none were in their 60s and 70s. Ben Franklin was an old founding father back in the day. But, Jefferson and Hamilton, all those people, Madison, they were young and they were super educated, right? They spoke Latin. They had all these libraries full of books of Greek philosophy that Congress had access to, and they were really up on the latest writings from Europe about thinking about the social contract and the Enlightenment and human rights and things like that in a way that, let's just say, our current political leadership is not on either side of the aisle. So we've gotten away from that highly educated, we were in the United States, for all of its flaws of the current system, for all the flaws the Constitution has, we were really lucky in many ways to get people who wrote it who were very smart and also very high-minded. They had their interests in mind, but they really were earnestly trying to put together a system that they thought would work. We all know that there were failures of that system. The most obvious one is the fact that it didn't include slaves or women or et cetera, and you can argue whether or not it possibly could have, but it doesn't matter. The point is, for the present argument, if we tried to sit down and write a constitution now just by voting people into some sort of congressional assembly or constitutional convention and had them write it, I would be horrified at what might come out. I would have very, very low expectations at what might appear from that. I don't know, mandatory gun ownership or something like that. I don't know what it would be. But it would be nice if the discourse that we had in our current political system was a little bit more elevated. I don't know how to get there. I have no practical suggestions along those lines. Sorry about that. Alex B. says, if Jurassic Park were real and an escaped T-Rex was hunting down humans trapped in the park, would you support killing it to save humans, even if it was the last of its kind? Well, yes, that would be pretty easy. Both for sort of moral, ethical reasons. I think that the inner life of a human being is much richer and more valuable than that of a Tyrannosaurus. But also, if Jurassic Park were real, by construction, we just made a T-Rex. So it's not the last of its kind. We can just make another one. I know that's sort of cheating around your thought experiment there. But in general, I take human life to be more valuable than the lives of other animals. That's not absolute. There are spectra here. There's a continuum. We're not completely distinct from other kinds of living beings here on Earth. We're all part of the same family, et cetera, et cetera. But having said that, I do think that I think that human beings are just different in the real world for practical purposes. Jesse Rimler says, in the May AMA, you answered a question regarding the Russian invasion of Ukraine. In your answer, you stated that Noam Chomsky had recently called for Ukraine to lie down and take it and surrender to Russia. I've read Chomsky's statement, and I don't think your comment reflects his statements. To be fair, you said it was a rough paraphrase. Here is my summary of Chomsky's position. The U.S. should use its influence to encourage a settlement between Ukraine and Russia in order to end the war. He notes that this diplomatic solution would not be just, but that the results of international diplomacy rarely are. He says that Ukraine's resistance under Zelensky has been honorable and that Russian aggression is criminal, not unlike our invasion of Iraq. He critiques the U.S.'s current stance, which is to support the war down to the last Ukrainian, which will almost certainly lead to protracted conflict that kills more Ukrainians and terrifyingly raises the chances for nuclear war. Do you believe this position to be unreasonable? Well, I don't know whether it's reasonable or not, but I believe it to be wrong. And the reason is it's not a matter of supporting the war down to the last Ukrainian. It's a matter of supporting what the Ukrainians want. I'm in favor of thinking less about what is in the United States' interests in this particular question and thinking about what is in the interests of the people in Ukraine. And they want to resist. So I'm in favor of it. I'm in favor of helping them resist if that's what they want. I think that the invasion was completely illegal and immoral and wrong. And it should not be allowed to stand if there's any way of resisting it. And the Ukrainians so far have been really, really good at resisting it. I think that we should count our lucky stars that they have been that good and give them all the help that we can. Nicholas Worsley says, if and when quantum gravity is figured out, do you think relativity will be taught as a step like Newtonian physics, or is it likely we don't need it at all? Well, relativity is clearly going to be taught like Newtonian physics, and this is a feature of how science works. It's not just one theory that is right and all the other theories that are wrong. There are theories that are right as limiting cases of other theories. So when quantum gravity is figured out, it will almost certainly be the case. In fact, I'm tempted to say certainly, if I were indulging in such rhetoric, that there will be a limit, a classical limit of quantum gravity that looks like general relativity, right? How do we know that? Well, because general relativity is super duper successful at accounting for things like gravitational lensing, the orbit of Mercury, the prediction of black holes, gravitational waves, the expansion of the universe at early times, and so on and so on. So it is absolutely, completely respectable to use classical general relativity rather than quantum gravity, even if quantum gravity is figured out in the regime where classical general relativity applies. And the thing is that the regime where there is gravity noticeable at all is almost entirely in the regime where classical general relativity applies. So it's really kind of the other way around. If we figure out quantum gravity, that will be great. That'll be great for physics. It'll be a huge monumental intellectual achievement. But as a practical matter, if you need to do a calculation in astrophysics or cosmology, you're just going to use classical general relativity. Just like if we want to fly a rocket to the moon, we use Newtonian physics perfectly well. Mark Scheuern says the last the 3-volume Feynman lectures on physics represented quite a radical departure from the usual freshman physics textbook. It seems to have been largely a failure since, as far as I know, no introductory physics textbook since much resembles it, even if it's much beloved by more advanced students. I'm curious what your thoughts are on the books and whether there might be a better way to present introductory physics rather than the traditional way. So I think that the Feynman lectures are not a failure, but they're not a model for other physics textbooks. I don't think that's a very useful way to think about them. They are used by plenty of people, by students trying to learn physics, by teachers who teach freshman physics to get ideas for clever ways to teach things, but they're at a slightly higher level than you want for a traditional physics curriculum. And also there's no problem sets in the books themselves. There's other books that have come out since that have problems. And, Feynman does like to ramble on sometimes. And he also has his own individual things that he's interested in, right? That are fascinating. They're all really cool, but they kind of slow you down if you're just trying to get to the basics of physics you were trying to teach the first year students. So I think that they're extremely successful as what they are, which are textbooks in physics that are good to dip into. In many areas, that's true. There are many books in, general relativity or quantum field theory or whatever that are wonderful reference books and books to have on your shelf once you've learned the subject, but not the best books to learn it from the start. In terms of, is there a better way to present introductory physics? I honestly don't know. I have never taught introductory physics. I have not taken it for many, many years. I have no strong thoughts on it. I would be happy if there were more glimpses of the future in introductory physics courses. So not just here as an inclined plane, but a little bit of an introduction to the frontiers of physics to get people a little bit more excited. But that's just sort of a bonus extra thing to put in there. It's not really a restructuring of the basic curriculum itself. Kathy Seeger says, in the last chapters of Something Deeply Hidden, you write about an emerging metric of space from the entanglement structure of the quantum state. From there, you go on to defining areas, a collection of degrees of freedom to be proportional to their entanglement entropy, and that leads to a geometry of space. Could this approach be run on a computer simulation/model, or is it more likely a highly theoretical Laplacian demon thing, for which you have to know all the specifics beforehand to get something out of it? I think it's somewhere in between. There's no obstacle in principle to running this kind of idea on a computer, but it would be very small scale. The thing about that we think is true about space-time, if it does emerge from quantum mechanics, is there's a huge number of degrees of freedom in every very, very tiny region of space. I forget what the number is. I think I once figured out that in a cubic centimeter of space, we're postulating something like Hilbert space of dimension 10 to the 10 to the 60th. Right? So that's a lot of numbers, a lot of degrees of freedom that you're not going to be able to put on a computer anytime soon. So what you really be doing is a very, very highly constrained toy model with just a few degrees of freedom, because simulating quantum things on classical computers is famously hard. And that's one of the reasons why quantum computers were invented in the first place. But in principle, the equations should work out such that the structure is similar to the rest of physics, where you have initial conditions and you can evolve them over time, or you just try to solve the quantum equations through the path integral or whatever it is. But it's the same kind of approach as in the rest of physics. Jordan Dansby says, can you speak to the quantum mechanics of climate change, specifically the quantum concepts at play, if any, in the manner in which CO2 molecules trap heat energy radiating from the Earth's surface? So the short answer is no. I mean, there are obviously quantum mechanics ideas that are required to understand why certain compounds in our atmosphere let certain wavelengths of light through and trap other wavelengths of light. I mean, the basic idea of the greenhouse effect is that we get visible light from the sun. We put things in the atmosphere that are transparent to visible light, but opaque to infrared light. And it's the infrared light that is actually emitted back from the Earth. So you let light in, but you don't let light out, and we heat up. That's the greenhouse effect. Now, you can derive, in principle, what frequencies of light will pass through different kinds of gases from the principles of quantum mechanics. I myself can't do that. I mean, I could do that if you sat me down with a textbook and gave me time, I could do it, but I haven't thought about those calculations mostly forever, or even if I have, it's been a very long time, so I can't do it off the top of my head. But also, more importantly, the reason I wanted to answer the question is it doesn't matter. It really doesn't. Once you know the answer, once you know the spectrum of light that passes through these particular kinds of gases, which you can get just empirically, just experimentally, just put the gas in a jar and pass light through it and see what spectrum goes through and which one is absorbed. That's all you need. You don't need any quantum mechanics for that. And that's all the science that you really need at the simple. It's the simplest level of science you need to talk about climate change and the greenhouse effect, etc. So this is, again, I don't want to harp on the same things over and over again. This is emergence at work. You don't need to know the microphysics to understand what's happening at the macro level. Once you understand the interaction of light and the gases, that's what you need for the higher level computations, such as climate change. Bruno Teixeira says, isn't strong emergence kind of anti-naturalist? What am I missing? I don't think it's necessarily anti-naturalist. So strong emergence is the idea. Well, let me back up a little bit. I'm not sure that people give very good definitions of strong emergence. And as I've said many times, the sad thing about discussions of emergence is they all devolve into discussions of the definition of emergence, which is incredibly boring. And so I don't kind of want to worry too much about the definition. So let me tell you my idea that comes to mind when someone says strong emergence. We imagine that there is a way of thinking about something in the universe by dividing it up into constituents, right? So you can think about the table in front of me as made of atoms, or you can think about society as made of people, okay? In either case, you're taking a big system and dividing up into a set of interacting smaller systems. And then weak emergence is supposed to be the idea that we have a theory of the individual constituents, the atoms or the people or whatever, and we put that all in a computer, that theory, and in principle, if we had a sufficiently powerful computer and the theory of the individual constituents, we could put them all together in an initial condition, run it, and we would get the right answer. But we could also just discuss the collective at the same time. So I can discuss the tensile strength and the color and things like that of the table in front of me without knowing anything about the atoms. And at the same time, if I did know about the atoms, I could put them on a computer and derive the properties of the table. That's weak emergence. Strong emergence is you have a theory of the fundamental constituents, but if you put it together, put just a bunch of constituents individually on a computer and asked what happened, you would not get the right answer for whatever reason, okay? So that could be an anti-naturalist position because it could be that you're saying you don't get the right answer because something spooky and ineffable comes in and changes the behavior of the system. That's one possibility. But another possibility is that what you thought was a completely comprehensive theory of the constituents actually wasn't. Maybe the correct theory of the constituents is different if the constituents are just talking to each other one-to-one versus being embedded in some larger collection, okay? That would be in principle, completely naturalist kind of strong emergence. And again, I'm not completely sure that makes sense, but I can at least imagine it. I don't know that it doesn't make sense. It doesn't happen if your tiny systems are atoms or molecules or elementary particles, because those obey local laws of physics, as we talked about earlier in the AMA. They don't care whether they're in an atom or a rock or a table or interstellar space. All the electron cares about is what the fields of its other fields are doing at the same point in space-time. So there's no room for strong emergence there. But if your small systems are something like people, then maybe the relationship is more complicated. We have a very clean, crisp relationship between atoms and gases or solids. The relationship between people and societies is a little bit messier. Where do you draw the boundaries, and how do things affect each other and stuff like that? So I'm open to the possibility that when the individual constituents are themselves complex, there might be situations in which strong emergence is a useful way of thinking about things. I don't know for sure that there is, but I'm open to that possibility. Gregory Kusnik says, since we can't know the details of our present microstate, we're forced to accept that there's a set of possible past microstates from which our current state could have evolved. It seems to me that observations of events in the present constrain the set of past microstates in much the same way they constrain future microstates. But the conventional view of causality says that it only flows in one direction from past to future. What then should we call the backward-flowing kind of constraint? Well, as I've discussed before, you're right that from only our observations of our present macrostate, you would be able to say the same kinds of things about the future and about the past. The present microstate implies more or less similar sets of possibilities for one direction of time and the other. But that's not the universe we live in, or at least that's not all we have access to. We also have the past hypothesis. We also know that the early universe had low entropy. So that's an extra feature we have about the past that we don't have about the future. There is no known or plausibly conjectured future boundary condition that ties things down at all. So it's not that there is something intrinsic to time that lets us take the current microstate and talk about its past and future development differently. It's that we have an extra piece of information in the past. And it's from that extra piece of information, the low entropy past, that we derive the fact that at the emergent higher level, there are things called cause and effect relationships that flow from the past to the future. So I think what you're thinking of is just the past hypothesis. Ross Hastings asked a priority question. I've been sufficiently troubled by your conversation with Sally Haslinger that I've waited some months before commenting, and in the light of global events since, it sits all the more uncomfortably today. I'm a lifelong leftist who believes that woke ideology is dangerous, divisive, elitist, and actually racist, and I would love to hear some balancing commentary on your show. My question today is, will you consider talking with an alternative voice? The short answer is no. I will not consider talking with an alternative voice about those specific issues, about anti-wokeism or anything like that, for a number of reasons. I mean, first and primarily, a sufficient reason is that's not what this podcast is about. Mindscape is about trying to understand the world, trying to understand, hopefully, eternal truths. Eternal might be an exaggeration because political, economic, social, literary truths still count, and those are a little bit more ephemeral. But it's about analysis and about understanding difficult issues. It is not about fighting whatever culture war battle is occupying people's attention at the moment. I'm happy to have people on the show who are active in such battles on either side, but I'm not going to talk to them about that, okay? I actually, I think that such battles are important. I don't want to discount them. There are many important things that we don't do here on Mindscape. Here we're trying to do something different, and I like the fact that we're trying to do something different. I will have Sally Haslinger on the podcast, but it wasn't a rant about wokeism. We were talking about the social construction of reality. This is a crucially important philosophical topic. I had Neil Ferguson on the podcast, and he kept wanting to talk about cancel culture, but I was more interested in talking about history and complexity and organizations and things like that. We had Yasha Monk on the podcast, who has been outspoken on these issues on the other side also, but we talked about liberal democracy. That was what he's an expert on, and we hope to understand the world a little bit better. So that's what I'm all about here. Also, however, I want to be completely honest here. In my view, the intellectual case, such as it is offered by these anti-woke folks, is incredibly weak and unpersuasive, almost hilariously so. And I do want to have different perspectives on the podcast, but I don't want to have any perspective on the podcast. My rule has always been I want to bring people on the podcast who have something interesting to say, even if I disagree with them very deeply, like, Philip Goff talking about panpsychism. I completely disagree, but I do think it's an important thing to think about. It's a perspective that shouldn't be dismissed. I'm not going to have astrologers or flat earthers. And to me, this is the category that these anti-woke people are in. In my view, discrimination and systemic biases are just extremely real and perfectly obvious, a truly horrible aspect of life in the modern world. I mean, I can't see how someone can deny the existence of these things and be outraged by them and want to fight against them. I think that what we need to do is the hard work of figuring out where these systemic biases are, fighting against them, and more importantly, recognizing the biases within ourselves that cause us to deny their existence. People go bending over backwards to sort of ignore the discrimination that is right in front of them if it makes them feel bad, and I think that's kind of silly and embarrassing, and we need to do better. That's not to say I will not disagree with the tactics used by people on the more woke side, if you want to call them that. I very often do disagree with the tactics used, the strategies, but my goals are entirely aligned with people who are against racism, sexism, transphobia, etc. If my goals are the same as theirs, then fundamentally we're allies. And when I disagree with them, it is in the service of better attaining the goals. So I'm much more of a free speech absolutist than a typical woke person is. I want to allow all sorts of speakers on campus, even people who I think are truly terrible. If some tiny group of students on campus wants to invite a terrible speaker, then I'm entirely in favor of that. And I don't even think you should heckle them. I think you should let them give their talk. But the reason why I think that is because I think the principle of letting anyone give talks and hearing their voices is fundamentally a principle that will ultimately help fight discrimination and racism, etc., rather than using silencing as a tool. I think that's just a mistake of strategy. But the fact that I disagree on strategy doesn't mean I disagree on goals, and I don't treat those people as my enemies or the people I'm fighting against. So, I mean, I think if a person with a public platform says that they're, let's say, anti-racist, but then you listen to how they spend their time on their public platform, and they're never complaining about racism, but they're often complaining about the excesses of anti-racism, then, effectively they're fighting for the other side. Whatever may be lurking inside their heart, their actual actions speak differently. And so I'm just not interested in giving them an even bigger voice. And that's the final thing I will say is there's no shortage of places on the internet where you can hear that perspective being said, right? It's not like some plucky minority which can't get its message out, the anti-woke campaign or whatever you want to call it. Plenty of places where you can hear that perspective being articulated. If anything, what I want to do, if only sort of by example, is to reclaim the language of logic and truth and facts, which has been appropriated sometimes by these people. And I think it's been wildly misappropriated. I think that they're denying science. They are not being rigorously logical and careful. They are using a lot of sophistry to prop up a lot of very questionable points of view. So I want to be a counterexample. I don't want to help them out. They don't need my help. They're very, very noisy. They're very, very ubiquitous across these platforms. So what I am standing for here is something very different than that. Brian Tidmore says, if humankind were to advance technologically enough to build a machine that could manipulate gravity, do you have any guesses what such a device might look like? Would it need to be capable of manipulating quantum fields/particles, or would it function in ways scientists cannot presently imagine? Well, there are machines that manipulate gravity. They're called masses. Large objects manipulate gravity by causing gravity. I think that there is a possible conceptual error in thinking about manipulating gravity in a way that is different from simply putting a heavy object there and let it attract things, because that's really all we can do when it comes to manipulating gravity. The reason why that we think that maybe we can do otherwise is because the other example that we have in nature of a long-range force is electromagnetism. And so we sort of train ourselves on electromagnetism and think maybe someday we'll be able to do similar things with gravity. But the huge difference is that for electromagnetism, we have positive charges and negative charges. For gravity, roughly speaking, we only have positive charges. Everything attracts, right? I say roughly speaking because there's some little footnotes, but for technological purposes, those footnotes are not very relevant. Roughly speaking, gravitationally, everything attracts everything to everything else. Gravity is a very dumb, simple force in that way. Whereas electromagnetism, from the simple fact that there are positive charges and negative charges, is sort of infinitely manipulatable because you can create sets of many positive charges and negative charges and have some of them go in motion and so forth and create all sorts of very delicately tuned electric and magnetic fields. With gravity, you just can't do that. With a positive charge and a negative charge, you can cancel out electric fields in different places and amplify them in other places. With gravity, all you can do is create more of it or less of it by taking an object and move it further away. So roughly, I think that as far as we currently understand gravity, we're not going to be able to manipulate it in the same way that we can manipulate electromagnetic fields. Timothy Carroll asks a priority question. I'm very aware of your presentation of the particle at the end of the universe and the halls of the Royal Institution. It's been 9 years since your beautiful explanation on the hunt for the Higgs. Some physicists feel that the construction of a new particle collider with higher power is not the best use of research dollars. Do you feel the same way, or could you justify this extreme financial burden for a new facility? I think it's an important question and a difficult question. But it's not a question you should expect an objective answer to for two reasons. Number one is we do not have a fixed pot of money that we sit down and say, what is the best way we can spend this on research, right? It's not like there's a fixed number of dollars and we say, okay, biology gets so many and chemistry gets so many and particle physics gets so many. This is a lesson that has been beaten home over and over again when we've had an expensive science project that people have campaigned against on the theory that the money could be better spent elsewhere. And the project gets canceled, and guess what? The money does not get spent on science at all, because there's no rule that the amount of money spent on science has to be fixed. So generally, when you have these giant particle accelerators or telescopes or whatever, the question is not, do you spend it on this or do you spend it on other science? The question is, do you spend it on this or do you just spend it on something completely different, not scientific at all? And the other thing is, this is not a decision made by the world, right? These facilities are built in countries, and the countries or the groups of countries that build them generally decide what they want to do with the money. So if some country, if China or Europe or whoever wants to build a giant particle accelerator, that's the choice that they are going to make or not make. Again, it doesn't come out of the money from other countries. And finally, I think I said two things, but it's really three things. There is a difference between building a giant particle accelerator and doing other kinds of experiments. Namely that the kinds of answers you would get, the kind of things you would learn from a giant particle accelerator are just not achievable in any other way. You can do experiments in, cosmic rays or tabletop experiments, and maybe you will get a hint of the existence of other particles, but you can't figure out what particles they are. You just can't get the detailed close-up look. And there's some kinds of new particles that you just can't discover in that indirect way. You just have to smash other particles together and see what comes out. That's really the only thing that you can do. So when you were thinking about whether or not it's worth the money, and again, I have no idea whether it's worth the money because I don't know what the options are in spending the money otherwise. But when you're figuring that out, it's just a mistake to compare it to say like, well, I spent $1 million on this and got a certain research output, but this is costing $10 billion. Is it really 10,000 times worth 10,000 of the original experiment? Because the original experiments don't scale like that. If you have some really, really good tabletop atomic physics experiment that costs $1 million, it won't be 100 times better if you spend $100 million on it, or if you do 100 of them, right? some experiments can be done for small amounts of money. Some just need large amounts of money. And in the current state of technology, you can't do high energy particle physics in a very effective way without spending a lot of money. So I think it is a unique kind of project where there's lots of justification for trying to do it. On the other hand, the justification is not cut and dried because unlike with the Large Hadron Collider, we don't have a target. Right? With the LHC, we had the target of the Higgs boson and more generally the electroweak scale, where we were hoping to find things. We only found the Higgs so far. We're still hopeful to find something new, but we haven't yet. Whereas if you build the next collider without having found anything new at the LHC, you're just going on a fishing expedition. If you find something, it will be incredibly important, the first super direct, obvious evidence of physics beyond the standard model, but I can't promise you or even give you good odds that we will find something for any particular machine. So that is a strike against spending a lot of money on these machines. It's a hard call to make, and I'm glad that I'm not the one making it. Eric Stromquist says, when people have asked you in earlier AMAs about possible mathematical realism about the world, you've said that you are a reality realist instead. My question is, but what about the supervenience of low-level physical facts and structure on the mathematical structure of whatever will be completed physics? To clarify, I focus on mathematical structure rather than mathematics because mathematics is a human endeavor that may be merely nominalistic, while mathematical structure is what human mathematics purports to describe. Atomistic objects like points in set theory or category theory having no intrinsic properties, but only relational properties with other such atomistic objects. The world's actual structure is mathematical because it would in turn supervene on the correct mathematical symbology of completed physics. So I'll have to confess I just don't know what this means in some sense. I know that people have made claims about physical reality being in some sense intrinsically mathematical, whether they're saying that it is math in some sense, like Max Tegmark might want to gesture toward. I just don't understand at all. But even the slightly weaker claim that somehow the physical world is a mathematical kind of structure, I don't know what that means. I don't know what the difference is between a mathematical kind of structure and a non-mathematical kind of structure. I mean, is an apple a mathematical structure? Because if I have 2 apples and get 2 more apples, I have 4 apples? I just don't know what it means. I know what it means to say that I can use math to describe physical structures. That's what I do all the time. That's what physics does, and I'm very happy to do that. But to somehow attribute mathematicalness to a physical structure, I just don't know how to do that or what it means. So I don't think that there is any issue here in my own mind. I could be missing something. I'm not claiming to be a super expert on this stuff, but that's how I think about it. Jeff B. says, I was chatting with a friend who was interested in physics, and he wrote the following. My theory is that the universe is an inside-out black hole, and the event horizon is the edge of the observable universe. This explains the redshift of light we see, since black holes also have light redshifted around them. I knew there were a few things that didn't quite seem right about this, but I usually listen to you for quantum stuff rather than the cosmology stuff, so I wasn't exactly sure how to respond. Can you respond for me? Well, look, that's not a theory. To say the universe is an inside-out black hole is not a theory. For one thing, it doesn't make sense. There's no such thing as an inside-out black hole. I don't even know what that means, okay? The universe is described by a cosmological metric to very, very good precision. I think the deeper issue here is that, well, there's a whole bunch of issues. One issue is that if you believe general relativity at all, which presumably you do if you're talking about black holes, right? They're a prediction of general relativity. If you talk about black holes and event horizons and black holes redshifting light, if you believe all that stuff, presumably you believe general relativity, then in general relativity, the universe is expanding or contracting, and empirically it's expanding, and that is the redshift. There's no need for an extra explanation. You cannot say I believe general relativity, but I don't think the universe is expanding or contracting. That's just not how the equations work, okay? So we already have explained this. You don't need a new explanation. Furthermore, and at a more detailed level, the redshift that is associated with galaxies and quasars and so forth is not just one phenomenon all by itself. There are many phenomena that fit together. The expansion of the universe, the early universe and nucleosynthesis, the growth of structure in the universe, the fact that there are gravitational time delays as well as gravitational redshifts. There are many phenomena, all of which fit into the usual kind of picture. And if you say, well, the usual kind of picture is not right, I have a new picture, you got to re-explain all of those phenomena, okay? So if someone says, I have a theory about the universe that is new and exciting, just say, all right, in your theory, what is the ratio of hydrogen to helium produced in the early universe? And when they tell you that, ask them what the amount of deuterium and lithium is, okay? Until you get to that level of detail, which the standard model explains very, very well, it's not really worth taking alternative theories very seriously. Kevin O'Toole says, whenever you discuss a quantum field like the electron-positron field, the mathematical object I picture is basically like the electric field. I imagine a vector, or at every point in space, or maybe a matrix or something. However, I know this picture can't possibly be correct because of entanglement. Data at each point is a local description, so unless I'm missing something, it can't encapsulate correlations that exist between distant points in space. So then what is the correct mathematical structure to be picturing? This is going to be one of my deflationary answers here. You can't picture it. Sorry. No one ever does picture it. It's not just you. Leonard Susskind or Edward Witten or Nima Arkani Hamed are all picturing something like the electric field when they picture a quantum field. They know it's not right? They know that there are other ways of thinking about it that are purely mathematical, right? They can calculate the correlation functions, or they can calculate the entanglement entropy between different regions of space. They know how to manipulate the thing, but our visualization capacities are just not up to the task. We don't have enough dimensions in our brain to really think about entanglement between a whole bunch of quantum fields at different points in space. So what you should be thinking about is the mathematical description of the quantum state of these fields. That, it might be not what you want to think about, but that's the correct way of thinking about it. Kaimana Cook says, do you think there is something special and or real about the present? No, I don't. I mean, my present self has something real about the present, but my future self will have nothing special about the present moment. At every moment, there's stuff that exists, and that is the stuff that exists in the present moment. It's just a label. It's like saying, is there anything special about latitude 30 degrees north? It exists, but there's nothing special or ontologically distinct about it. Jim Murphy says, what are some of your favorite live music experiences? I've gone to a bunch of various kinds of concerts and so forth. I'm not nearly as big a music fan as some other people are, so I wouldn't get, don't have the depth of experience that some other people have. The best live music experiences have been at tiny little jazz clubs, right? When I was at Chicago, I used to go down to the New Apartment Lounge on the South Side and listen to Von Freeman play on Tuesday nights, deep into the evening, and, sitting 5 feet away from the band, right? And not the most elegant surroundings, but a wonderful melting pot of different kinds of people, locals from the neighborhood, music aficionados from around the world, students from the University of Chicago, and so forth. And it was just tremendous fun. And the band was amazing, improvising in ways that you don't get to hear much on the radio and things like that. So I would have to pick that as my favorite kind of music experience. Don't get it that much here in Los Angeles, I'm afraid. Brendan Kruger says, if your brain was strong enough to envision future events down to the most fundamental scale of physics, would calculating a future state of the universe in your head temporarily create a new universe? So I get the question, and the initial feeling is to dismiss it, but I don't think it's an easily dismissed question upon further reflection. But I think the idea here is that if you're literally simulating the complete behavior of everything in the universe, whether it's in your brain or in a computer, does that count as a universe, right? Because you're simulating the whole thing that is going on. So this is the point of view advocated in David Chalmers' new book. We had David Chalmers on the podcast a while ago talking about consciousness, but his new book, Reality Plus, is exactly advocating for the idea that if you simulate something exactly, then that thing that you've simulated exists in that simulation. And I get that. I'm sympathetic to that. I haven't thought through all the pluses and minuses, so I can't promise you that I would stick by that position. But in some sense, I think the answer to your question is yes. But then there's a separate thing, which is the attitude one should have towards such questions, which is, you're cheating a little bit. You're cheating a little bit by asking it, because you're literally saying, if your brain was strong enough to envision future events down to the most fundamental scale of physics, okay? Your brain is not strong enough, nor will it ever be, nor could it be. Because the point is, you basically need your brain to be as large as the universe to do that at the level of simulating the entire universe. So what I'm saying is that in order to physically realize this kind of simulation, you basically would be creating a new universe. It's not just a matter of doing, mental exercises to improve your thought processes. It's a much more dramatic kind of thought experiment that you're doing here. And I think that we are a little bit too quick to generalize the fact that, I can visualize in my head a game of chess or checkers. Therefore, why can't I visualize everything in the universe? It's just a matter of degree, right? Well, sometimes the matters of degree matter by a lot. And I think this is the case. Mikhail Sirotenko says, I'm now reading a chapter about chaos in a book about complexity. After giving an example of an equation that can lead to an unpredictable result with any infinitely small change of the input, the author concludes that this implies that perfect prediction a la Laplace is not possible not only in practice but also in principle. But is it? If we build such a model of the universe that takes only rational numbers as initial conditions, we still make exact predictions, right? A lot of this depends on what you mean by in principle and what you mean by prediction, okay? It remains true, even in the presence of chaotic dynamics, that exactly specified initial conditions lead to exactly predictable future conditions, okay? That's what Laplace's demon says. What is being traded on in discourse like this is that you never have access to exact initial conditions for any real physical system. You can imagine, counterfactually, if the initial conditions were such and such rational numbers, then you could make the prediction. But the point being made is you never know that that is the initial condition. And both things are true. It is both true that there is determinism, that given the exact initial conditions, the later final conditions are exactly predicted, and that you don't have access to that. I personally think that this has nothing to do with chaos theory. I mean, people make it into a big new distinction that, we discovered this when we discovered chaos theory. But look, Laplace never thought that in practice we were going to be able to have perfect information. And without perfect information, you can't make perfect predictions. The dynamics of chaos theory help you quantify how bad your predictions are going to be, but we always knew they wouldn't be perfect because you don't have access to that information. So I don't think that there's any big conceptual shift brought on in the determinism discussion by the fact that we now know that some dynamics can be chaotic. Andrew Goldstein says, I'm probably conservative when I estimate the number of academic, communication, writing, researching, and interviewing activities that you are engaged in. So I ask, how do you embrace and maintain this extensive and diverse schedule, not to mention your personal life, where you presumably get to enjoy the realities of nature that you so exquisitely articulate? I don't know. Thank you for the implied compliment there. But as I said before, I've been fortunate enough to be able to shape a life, a world, a job where I can do a little bit of all these different things that I like. It means that I'm not nearly as devoted to any one of them as I could be, right? I don't spend as much time doing physics research as I could. I don't spend as much time and effort writing books as I could, or even the podcast, right? I try very hard when I take on these new activities to limit them, to limit the amount of time it would take. So for the podcast, it's literally limited to 1 day per week. I produce one podcast a week, and producing a podcast takes about a day. If it ever grows more than that, I would not be able to do it. So, I could do better about editing or whatever, musical cues, I don't know, but I'm not going to do that. This is what it's going to be. Now I have a new job that involves teaching and other new responsibilities that I didn't have in the last couple of years. So something might have to go. Something else might need to be downshifted. We'll have to see about that, but it hasn't quite hit yet. I certainly don't have any secrets or magic elixirs to get a lot of things done. I've just sort of been stubborn enough to insist that I can do them, and lucky enough to be able to be given the opportunity to actually make it happen. Okay, final question. Humberto Nani says, during your podcast with Leonard Susskind, He answered your question about his activities in the realm of writing the theoretical minimum books by talking about how he wanted to teach real science versus crackpotism to his parents and to his parents' friends. It's a very touching story. So besides us, the general audience that is interested in your videos and books on the biggest ideas, is there a particular set of persons you are targeting? Short answer is no, or at least not in general. A longer answer is I target different sets of people with different things that I do. So when I write a textbook in physics, I'm targeting one set of people. When I write a technical paper in physics, I'm targeting a different set of people. When I'm writing a book, it's a different set of people. When I'm doing a podcast, it's yet a different set of people. When I tweet, it's yet a different set of people. As I've said many times in many different circumstances, that's not the only way to do it. You can I'm a big believer in the power of specialization in the right circumstances. I think that the problem with specialization is when everyone is a specialist. I think that a healthy ecosystem needs both generalists and specialists. And this is true for science, but it's also true for communication. So I'm glad that there are some people who only write poems or only do podcasts or whatever, and only aim at a certain kind of audience. My audience is not universal. I don't aim at everybody every time. I'm not especially good at or interested in writing for kids, for example. It is more my style to assume some basic background knowledge and maturity. Sometimes the level is different. In the biggest ideas in the universe, videos and books, it's assuming more of the reader than previous books have. It's not assuming necessarily background, but it's assuming a certain gumption in being able to go through these equations and really try to figure out what they're saying. And not everyone wants to do that, and that's perfectly okay. I would actually like to someday write a book or some books that are aimed at an even bigger audience, an even wider audience than what I've written so far. Probably my most pick-upable book it was The Particle at the End of the Universe about the Higgs boson. But still, there are chapters on gauge symmetry and quantum field theory in there. The big picture was I tried to write it at a very accessible level, but it covers so many things that it's not everyone's cup of tea. I would like to someday write just a short, sweet book that had no equations in it, that got something important across, but was, attractive to a very broad audience. Haven't really done that yet. So the answer is there a particular set of persons I'm targeting? Different sets for different projects is the slightly weaselly but completely correct answer. Okay, thanks everybody for supporting the podcast on Patreon. It warms my heart to have you doing this. Hope you enjoyed the AMA. Talk to you next month.